All right, let's dive into the world of Chow Lam Recovery.
We'll be looking at a paper by Elizabeth Pratt and Kristian Ranestad. They ask a really interesting question. Can we fully reconstruct a geometric object just from its projections?
Kind of like figuring out a 3D shape just by looking at its shadow, right?
Yeah.
But here, things get a bit more abstract because we're dealing with objects in these spaces called Grassmannians.
Exactly. And these projections aren't just your everyday shadows. We're talking about very specific mathematical mappings that preserve certain geometric properties.
So maybe we should take a moment to explain Grassmannians. They sound a bit intimidating, but I promise the idea is pretty elegant.
You're right, it is elegant. A Grassmannian, written as Gr or K, Kristian, is basically a space that describes all the possible K1-dimensional subspaces you can have within an N1-dimensional projective space.
Okay, so for example, GR2 form would represent all the possible lines in a three-dimensional space.
Precisely. Think of it like a catalog of every single line you could draw in 3D.
And the paper focuses on subvarieties within these Grassmannians. These are the geometric objects, the shapes that we're trying to reconstruct.
Right. So the authors explore whether we can project a subvariety onto lower dimensional Grassmannians, kind of like taking different shadow images, and then use that information to perfectly rebuild the original subvariety.
It's like taking multiple X-rays of something from different angles and then trying to piece together its 3D structure.
That's a great analogy. And the tool they use for this reconstruction is called the Chow Lam form.
So tell me more about this Chow Lam form. What is it exactly?
Well, the Chow Lam form is a mathematical object that holds information about those projections we were talking about.
So it's kind of like a blueprint of the shadows.
Exactly. And the big question is, does this blueprint, this Chow Lam form, contain all the information we need to rebuild the original shape perfectly?
And what did Pratt and Ranestad find?
Well, it's not a straightforward answer. You see, in the world of projective varieties, we have this thing called the Chow form, and it's known to allow for perfect reconstruction.
But the Chow Lam form, which applies to these subvarieties of Grassmannians, is a bit more nuanced.
Exactly. Pratt and Ranestad show that sometimes the Chow Lam form does give us back the original subvariety, perfect reconstruction.
But other times,
Other times, we get these extra pieces that weren't originally there. They call them recovered components.
so the reconstruction isn't always perfect. That's a fascinating wrinkle.
It is. It's one of the key insights of their work. They show that Chow Lam recovery isn't a guaranteed slam dunk, and understanding why these extra components pop up is a big part of their paper.
Okay, so how do they even define this Chow Lam form? It sounds pretty complex.
Well, it involves a series of very carefully constructed mathematical objects. They start with projections between Grassmannians.
Projections like we were talking about before, right? Mapping objects onto lower dimensional spaces.
Exactly. And these projections are actually induced by linear maps between the projective spaces underlying the Grassmannians.
Okay, so it's like if we have a line in 3D and we project it onto a 2D plane, the image is still a line, but some of the information about its position in 3D is lost.
That's a perfect analogy. When we project a subvariety from one Grassmannian to another, we're mapping all its little pieces onto a lower dimensional space. And this process can obscure some aspects of its original structure.
So how do we bridge the gap between these projections and the original subvariety?
That's where a concept called the Chow Lam locus comes in. It's essentially the set of all linear spaces in the target Grassmannian that contain a projection of some linear space from our original subvariety.
I'm trying to visualize this. So it's like we're collecting all the points where the shadows of our original shape land in the lower dimensional space.
Precisely. It's like a record of all the target locations for our projections. And if this Chow Lam locus is a hypersurface, meaning it can be described by a single equation, that equation becomes the Chow Lam form.
So in a sense, the Chow Lam form captures the essence of where the projections end up.
Exactly. It's like a fingerprint of the shadow patterns. Now, there are cases where this Chow Lam locus is not a hypersurface. In those cases, Pratt and Ranestad simply define the Chow Lam form as 1. It might seem a bit arbitrary, but it's a necessary technicality to handle those situations.
Okay, so I'm starting to get the gist of how they define the Chow Lam form. But can you give me a concrete example to make it more tangible?
Of course. Let's imagine a curve, let's call it V, in GR24. This represents a bunch of lines in a three-dimensional projective space.
Okay, so our shape is a collection of lines twisting and turning in 3D space.
Right. Now, the Chow Lam locus for this curve would live in GR34, which is equivalent to something called the dual projective space, denoted P3A. Think of it as the space of all planes in P3.
So the Chow Lam locus is telling us about all the planes that contain at least one line from our original collection of lines.
Precisely. And if we can describe this collection of planes with a single equation, that equation is our Chow Lam form.
So in this example, the Chow Lam form is like a summary of all the planes that touch at least one of those lines in our original curve.
That's a great way to put it. And this connection between the Chow Lam locus and this idea of a dual variety holds more generally, which is one of the key results in the paper.
Okay, this is starting to make more sense. But how do we actually compute the Chow Lam form in practice?
Well, to do that, Pratt and Ranestad introduced something called primal and dual Plucker coordinates. Think of them as different ways of describing a linear space in projective space using coordinates.
Like different coordinate systems that are useful for different purposes.
Exactly. Primal coordinates work well when the dimension of the linear space is close to the dimension of the ambient projective space, and dual coordinates are used otherwise.
And are these two types of coordinates related?
Yes, you can switch between them using a simple formula.
Okay, that's good to know. So how do we use these coordinates to actually calculate the Chow Lam form?
Well, Pratt and Ranestad outline a computational procedure. First, you compute equations for something called the incidence variety, which is a space that captures pairs of linear spaces where one is contained in the other.
Okay, so we're looking at all the possible containment relationships between linear spaces.
Right. Then you essentially intersect this incidence variety with your original variety and project the result onto the space of larger linear spaces. That gives you the Chow Lam form.
So it's a multi-step process that involves intersecting and projecting these different spaces.
It is, and it can get pretty computationally intense, but it's a concrete way to calculate the Chow Lam form when you need it.
Got it. So once we have this Chow Lam form, the big question is, can we use it to perfectly reconstruct the original variety V?
Exactly. Can we go from the blueprint of the shadows back to the original shape?
And Pratt and Ranestad introduced this concept of a recovered variety, WV, which is basically what we get when we try to reconstruct V using the Chow Lam form.
Right. And the crucial question is whether WV is exactly the same as V, meaning perfect reconstruction, or whether WV contains extra points that were not in the original variety.
So are there cases where WV and V are not the same?
Yes. As we've discussed, sometimes WV is bigger than V, indicating that we've picked up some extra pieces along the way.
Those recovered components we talked about earlier.
Exactly. Pratt and Ranestad proved a very important theorem that gives a condition for a point to be part of this recovered variety.
So it helps us understand when these extra components might show up.
It does. It's all about analyzing the dimensions of intersections between a point and different parts of V. It gets a bit technical, but essentially it says, if this point truly belongs to the reconstructed shape, it has to intersect these other parts in a very specific way.
That's a really clever way to analyze the limitations of Chow Lam recovery.
It is. It gives us a tool to dig into those cases where the reconstruction isn't perfect.
This is fascinating stuff. So how do they illustrate all these ideas in the paper?
Well, they delve into some really interesting examples, showcasing cases where the Chow Lam recovery is perfect and cases where it's not.
What kinds of examples?
For instance, they explore ruled surfaces, surfaces that are generated by sweeping a line through space. They show that in certain situations, the recovered variety includes an extra line that wasn't part of the original surface.
So the Chow Lam recovery adds something that wasn't there before.
It does. And they also analyze cases involving the Hirsebruch surface, which is a specific kind of ruled surface.
And what happens there?
In those cases, they find that the recovered variety might include a fat point, which is basically a point with multiplicity. It represents a point that's been thickened in a certain way.
Okay, so again, we're seeing these extra elements appearing in the recovered variety.
Exactly. And they show that this fat point actually corresponds to a line that's part of the surface but wasn't part of the original curve that generated it.
So the Chow Lam recovery is picking up on this hidden line that wasn't explicitly part of the original construction.
Precisely. And these examples with ruled surfaces really highlight the potential for the Chow Lam recovery to add linear components that weren't there to begin with.
So it's not always a straightforward process of simply recovering the original shape. We have to be careful about interpreting what we get back.
Absolutely. And it gets even more interesting when they look at multi-ruled varieties. These are varieties that can be generated by sweeping multiple families of linear spaces through space.
So instead of just one set of lines, we have multiple sets generating the surface.
Exactly. And what they find is that these multi-ruled varieties can sometimes have different varieties that share the same Chow Lam form.
Wait, so multiple different shapes can have the same Chow Lam form?
They can. It's like different objects casting the same shadow.
That makes things even more complicated.
Yeah.
So the Chow Lam form doesn't always uniquely determine the original variety.
It doesn't. They illustrate this with the Segre embedding, which is a way of embedding the product of projective spaces into a higher dimensional projective space.
It's like taking multiple lower dimensional spaces and weaving them together to create something more complex.
That's a good analogy. And they show that using the Segre embedding, you can create distinct varieties that have identical Chow Lam forms.
So different weaving patterns, so to speak, can result in the same overall shape, at least from the perspective of the Chow Lam form.
Precisely. And this emphasizes that the Chow Lam form doesn't always capture all the subtle distinctions between different geometric constructions.
So we have to be very cautious about assuming that the recovered variety is the one and only solution.
We do. There might be other possibilities that fit the data equally well. And Pratt and Ranestad extend this analysis to multi-Segre varieties, which are generalizations of the Segre embedding, and find that this phenomenon persists in higher dimensions.
So this lack of uniqueness seems to be a fundamental aspect of Chow Lam recovery, not just a quirk of certain examples.
That's right. And it underscores the importance of understanding the specific context and the way the variety is generated when we're trying to reconstruct it.
This is all very thought-provoking. Now, I'm curious about another class of examples they mention, linear determinantal hypersurfaces. What are those, and how do they behave under Chow Lam recovery?
Linear determinantal hypersurfaces are a fascinating class of geometric objects. They're hypersurfaces, meaning they're defined by a single equation, but that equation comes from the determinant of a matrix.
So we're talking about surfaces or higher dimensional objects that are carved out by setting the determinant of a matrix to 0.
Exactly. And what makes them particularly interesting is that they're ruled by two families of linear spaces. You can generate the entire hypersurface by sweeping two different families of linear spaces through space.
So it's like having two sets of threads, and you can weave the hypersurface by moving each set in a specific way.
That's a great way to visualize it. And what Pratt and Ranestad discover is that this ruled structure has a direct impact on the Chow Lam recovery. They show that these two rulings lead to two pairs of varieties that share the same Chow Lam form.
So it's like the Chow Lam form sees these two pairs as essentially equivalent, even though they come from different geometric origins.
Precisely. One pair consists of the original hypersurface and its dual variety, and the other pair corresponds to the two families of linear spaces that rule the hypersurface.
This highlights how the internal structure of a variety, not just its overall shape, can influence its Chow Lam form.
It certainly does. And to illustrate this, Pratt and Ranestad connect this analysis to a classic example in algebraic geometry, the cubic surface.
A cubic surface is a surface in three-dimensional projective space defined by a cubic equation. It's a well-studied object with a lot of fascinating properties.
Exactly. And Pratt and Ranestad show that a cubic surface can be viewed as a special case of a linear determinantal hypersurface, where the matrix is a 3x3 matrix.
So there's a hidden connection between these two seemingly different objects.
There is. And they go even further, connecting the Chow Lam recovery for a cubic surface to a special configuration of lines on the surface called a double six.
A double six, what's that?
It's a collection of 12 lines on the cubic surface that are arranged in a specific pattern. You can divide them into two groups of 6 and no two lines within the same group intersect.
But each line from one group intersects 5 lines from the other group.
Exactly. It's a very elegant and symmetrical configuration. And Pratt and Ranestad demonstrate how this double 6 structure emerges naturally when you analyze the Chow Lam recovery for a cubic surface.
So the Chow Lam form is picking up on this subtle geometric arrangement hidden within the cubic surface.
That's right. It's a beautiful example of how the abstract properties of the Chow Lam form are reflected in the concrete geometric features of a surface.
It's amazing how these seemingly disparate concepts are all interconnected.
It is, and it highlights the power of algebraic methods for uncovering these hidden connections. Now, moving beyond specific examples, Pratt and Ranestad tackle a more general question. Do generic linear sections of Grassmannians exhibit residual components in their Chow Lam recovery?
So in simpler terms, they're asking if we slice through a Grassmannian with a random plane, can we perfectly reconstruct that slice using the Chow Lam form, Or will we end up with extra pieces?
Exactly. It's a challenging question to answer in full generality, but Pratt and Ranestad offer some valuable insights by examining specific cases involving curves and threefolds.
What do they find?
Well, for curves, they proved that if the curve comes from intersecting GR2n with a generic linear space, the Chow Lam recovery works perfectly, except when n equals 4.
Why the exception for n equals 4?
In that specific case, the curve is rational, which means it can be parameterized by a single variable, and that introduces an extra line in the recovered variety.
Ah, so it's a special case where the Chow Lam recovery isn't perfect.
That's right. But for threefolds, they analyze a scenario where the threefold is obtained by intersecting GR2 formal with 3 generic hyperplanes. And in this case, they prove that the Chow Lam recovery is indeed perfect.
So no extra components in that scenario.
None at all. Based on these examples, Pratt and Ranestad make a bold conjecture. They propose that for generic linear sections of Grassmannians, the Chow Lam recovery is always perfect.
So they're suggesting that those extra components we've been discussing aren't a generic phenomenon, but rather something that arises from specific structures or properties of the varieties.
Exactly. And if this conjecture is true, it would have significant implications for our understanding of the Chow Lam form.
It would mean that those extra components aren't an inherent limitation of the Chow Lam form itself, but rather a reflection of the special characteristics of certain varieties.
Exactly. And it highlights the importance of understanding those special characteristics if we want to fully grasp the intricacies of Chow Lam recovery.
So we've seen how sensitive this whole process is to the specifics of the varieties and their embeddings.
It's really fascinating how those subtle differences can have a big impact on the outcome of the Chow Lam recovery.
It reminds us that we can't just focus on the object in isolation. We need to consider its surroundings and how it fits into the bigger picture.
Absolutely. Context is everything in geometry. Now let's shift gears a bit and talk about another fascinating example that Pratt and Ranestad delve into: Schubert arrangements.
Okay, Schubert arrangements. Those sound familiar. Didn't we touch upon Schubert varieties earlier?
Yes, we did. Schubert varieties are fundamental objects in the study of Grassmannians. They're defined based on specific geometric conditions, often related to how a linear space intersects a sequence of nested linear spaces.
So it's like specifying how a line or a plane intersects a series of larger and larger spaces.
Precisely. And a Schubert arrangement is essentially a collection of Schubert varieties. Pratt and Ranestad focus on Schubert arrangements that arise from intersecting a Grassmannian with multiple Schubert divisors.
I remember we talked about Schubert divisors before. Those are like hypersurfaces in the Grassmannian, defined by a specific geometric condition.
Yeah, I've got it. For example, a Schubert divisor could be defined by requiring a line to intersect a given plane.
And what do they find when they look at the Chow Lam recovery for these Schubert arrangements?
Well, what they discover is that for certain families of Schubert varieties, the recovered variety contains additional Schubert components that weren't originally present in the variety.
So we're getting those extra pieces again, those recovered components.
We are, and these extra components are quite interesting because they're also Schubert varieties themselves.
So it's like the Chow Lam recovery is introducing more Schubert varieties into the mix.
Exactly, and Pratt and Ranestad delve into the details of why and when these extra Schubert components appear.
Do they have any specific results that help us understand this?
They do. They prove a key theorem that identifies specific Schubert types that are guaranteed to show up as recovered components for certain families of Schubert varieties.
So we have a way of predicting when these extra Schubert components are going to pop up.
We do, at least for certain families. To make this more concrete, let's look at a specific example they give. They consider a threefold in G245, which represents a collection of lines in a 4-dimensional projective space.
Okay, so our object is a collection of lines in 4D space.
Right. And this threefold is defined as the intersection of 3 Schubert divisors, which correspond to 3 generic planes in P4.
So our threefold is made up of all the lines that intersect all 3 of those planes.
Precisely. Now, what they prove is that the recovered variety for this threefold contains 6 additional components.
6 extra pieces.
Yes. 3 of these components are Schubert varieties of a specific type, representing lines that intersect the intersection of 2 of the original planes.
So instead of intersecting all 3 planes, these lines only intersect 2.
That's right. And the other 3 components are also Schubert varieties, but of a different type. They represent lines that are entirely contained within one of the original planes.
So even though our original threefold was defined by lines intersecting all 3 planes, the Chow Lam recovery is adding lines that only meet 2, or even just lie within one of the planes.
Exactly. It's a fascinating example of how the Chow Lam recovery can introduce these extra Schubert components that satisfy weaker conditions than the ones that define the original variety.
It's like the Chow Lam form is revealing hidden relationships between these Schubert varieties that weren't immediately obvious.
That's a great way to think about it. And they don't stop there. Pratt and Ranestad extend this analysis to higher dimensional Schubert varieties as well, demonstrating that these recovered components persist across different dimensions.
So it's a recurring phenomenon in the world of Schubert arrangements.
It seems to be. They even provide a table listing specific examples of recovered Schubert components for different values of k and I, where k is the dimension of the linear spaces in the Grassmannian, and I is a parameter that controls the complexity of the Schubert variety.
So they're really trying to systematically explore when and how these extra components appear.
They are, and they even go a step further by proving a general theorem that identifies the types of recovered Schubert components that are guaranteed to appear for certain families of Schubert varieties, as long as the ambient dimension is large enough.
So this theorem gives us a powerful tool for predicting the behavior of Chow Lam recovery for Schubert varieties in higher dimensions.
It does. It's a major step forward in our understanding of how the Chow Lam form interacts with the intricate geometry of Schubert varieties.
It's amazing how this seemingly simple question of recovering a shape from its shadows can lead to such deep and intricate results.
It's a testament to the power of algebraic geometry and its ability to uncover hidden structures and connections within seemingly simple geometric objects.
Now, I'm curious about how they explain the appearance of these recovered Schubert components. What's the underlying reason for this phenomenon?
Well, to get to the bottom of this, Pratt and Ranestad use a clever combination of dimension arguments and cohomological calculations.
So they're bringing in some heavy-duty mathematical machinery to analyze the situation.
They are. They delve into the geometry within a generic linear subspace that contains a point belonging to one of these recovered components.
So they're zooming in on a specific part of the space where these extra components are showing up.
Exactly. And by carefully analyzing the dimensions of various intersections and leveraging the tools of cohomology theory, they demonstrate the existence of common transversals within this subspace.
Common transversals.
Yes. These are essentially lines that intersect multiple of the defining linear spaces of the Schubert variety. And the presence of these common transversals forces the point to belong to the recovered variety, even though it might not satisfy the original conditions that define the Schubert variety.
So the existence of these common transversals is the key to explaining why these extra components are appearing.
It seems to be. It's a beautiful example of how a seemingly simple geometric condition, the existence of these common transversals, can have a profound impact on the algebraic properties of the Chow Lam recovery.
It really highlights the deep interplay between algebra and geometry.
It does. Now, it's important to acknowledge that not all recovered components of Schubert varieties necessarily conform to the types described in their theorem. For smaller values of I, that parameter we discussed earlier, there can be special cases where the recovered components behave differently.
So there are still some mysteries to uncover in this realm.
There are, but based on their observations, Pratt and Ranestad conjecture that for larger values of I, all recovered components of Schubert varieties belong to the types they've identified in their theorem. It's an intriguing conjecture that, if proven, would provide a complete characterization of the recovered components in this setting.
It would certainly deepen our understanding of the limitations of Chow Lam recovery for Schubert varieties. Now let's switch gears one last time and explore a very specific application of Chow Lam recovery that Pratt and Ranestad discuss: pository varieties.
Pository varieties are a fascinating class of subvarieties of the Grassmannian. They play a crucial role in understanding a concept from physics called the amplituhedron.
The amplituhedron, that sounds intriguing. What is it?
It's a geometric object that's used to calculate scattering amplitudes in particle physics. It essentially encodes information about the probabilities of different outcomes when particles collide.
So it's a geometric representation of a physical process.
Exactly. And understanding the projections of pository varieties is essential for analyzing the structure of the amplituhedron.
And how does Chow Lam recovery fit into this?
Well, Pratt and Ranestad observed that certain positroid varieties can be expressed as intersections of generic Schubert divisors.
Ah, so we can apply what we've learned about the Chow Lam recovery for Schubert arrangements to these positroid varieties.
Precisely. And they leverage this connection to prove a corollary that states that for odd values of n greater than or equal to 3, a specific positroid variety in GR2n actually exhibits a discrepancy between the recovered variety and the original variety.
So the Chow Lam form doesn't perfectly reconstruct this particular positroid variety.
It doesn't. It means there are recovered components in this case. And this result is significant because it shows that this phenomenon we've been exploring extends to this important class of varieties that are relevant to theoretical physics.
So the limitations of Chow Lam recovery might actually have implications for our understanding of scattering amplitudes and the amplituhedron itself.
That's a very real possibility. And Pratt and Ranestad encourage further investigation into the Chow Lam recovery of positroid varieties, hoping that it could lead to deeper insights into the structure of the amplituhedron and its implications for particle physics.
It's remarkable how this seemingly abstract area of algebraic geometry can have connections to such concrete physical phenomena.
It is. It's a testament to the interconnectedness of different areas of mathematics and science.
So we've explored all these fascinating examples where the Chow Lam recovery doesn't quite give us back the original variety perfectly.
And it really underscores the fact that this process is sensitive to so many factors.
Like the way the variety is embedded, its internal structure, and even the types of linear spaces used to generate it.
It's a reminder that even seemingly simple questions in geometry can lead to incredibly rich and nuanced answers.
And that the journey of exploring those answers can take us through some truly mind-bending mathematical landscapes.
Speaking of journeys, it's helpful to take a step back and appreciate the historical context of the Chow form and its generalization to the Chow Lam form.
It's always fascinating to see how mathematical ideas evolve and build upon each other over time.
Absolutely. The concept of the Chow form for projective varieties has a long and rich history, going all the way back to the work of Cayley in the 19th century.
Cayley was a true visionary in mathematics, making groundbreaking contributions to so many areas.
He was, and one of his key insights was the idea that projective varieties could be represented using a single equation, which we now call the Chow form.
So this equation essentially captures the essence of how the variety intersects with linear subspaces of different dimensions.
It's like a unique signature that identifies the variety based on its intersection properties.
And Cayley's work laid the foundation for a powerful tool in algebraic geometry.
It did. And his ideas were later expanded upon by Chow and van der Waerden in the 20th century, extending the concept of the Chow form to arbitrary projective varieties.
So they took Cayley's ideas and made them even more general and powerful.
Exactly. And their work solidified the importance of the Chow form as a fundamental concept in algebraic geometry.
Now, the Chow Lam form, which is the focus of Pratt and Ranestad's paper, can be seen as a natural extension of the Chow form to the realm of subvarieties of Grassmannians.
Instead of considering intersections with linear subspaces, the Chow Lam form focuses on intersections with Schubert varieties, those special subvarieties we discussed earlier.
So it's like taking the basic idea of the Chow form and adapting it to the more complex setting of Grassmannians.
Precisely. And this generalization opens up exciting new avenues for exploring the geometry of these subvarieties and their relationships to other geometric objects.
But as Pratt and Ranestad show, this generalization also introduces new challenges and complexities, leading to the fascinating phenomenon of recovered components.
It's a reminder that even when we try to extend a concept to a broader setting, we often encounter unexpected twists and turns along the way.
And those twists and turns can lead to some of the most intriguing discoveries.
Absolutely. Now, to really appreciate the depth of their findings, let's revisit some of the key examples they present.
One example that stands out is the case of a curve in GR2A4, representing a collection of lines in three-dimensional projective space.
Recall that the Chow Lam locus for this curve consists of all planes that contain at least one of those lines.
And if we can describe that collection of planes with a single equation, that equation becomes the Chow Lam form.
Right. Now, Pratt and Ranestad connect this example to the concept of the dual variety.
The dual variety being the set of all hyperplanes tangent to the original variety.
Exactly. And they show that in this case, the dual variety of the surface swept out by our curve is actually contained within the Chow Lam locus.
So there's a direct link between the Chow Lam form and the geometry of tangent planes to this surface.
There is. And if the dual variety and the Chow Lam locus have the same dimension, they're actually equal.
So in a sense, the Chow Lam form is capturing the essence of the surface's tangency properties.
It's like a fingerprint that identifies the surface based on how planes touch it.
It's amazing how such seemingly abstract algebraic concepts can have such concrete geometric interpretations.
It is. It's one of the things that makes algebraic geometry so captivating. Now, let's move on to another fascinating class of examples. Ruled surfaces.
Ruled surfaces are those surfaces that can be generated by sweeping a line through space.
You can imagine taking a straight line and moving it along a curved path, tracing out a surface as it goes.
And Pratt and Ranestad show that in certain situations, the Chow Lam recovery for a ruled surface might actually add an extra line that wasn't part of the original surface.
This happens because of the way the surface is embedded in the projective space.
So if all the rulings of the surface happen to intersect a particular line, that line can show up as an extra component in the recovered variety.
Exactly. It's like the embedding is creating a ghost line that wasn't part of the original construction.
So the Chow Lam recovery isn't just blindly reconstructing the original shape, it's also incorporating information about how that shape is situated in its surroundings.
It's a much more subtle process than it might appear at first glance.
And this sensitivity to the embedding can lead to some surprising results.
It certainly can. For instance, they analyze a specific type of ruled surface called the Algebraic surface.
And what do they find there?
They find that the recovered variety for the Algebraic surface might include something called a fat point.
A fat point. What's that?
It's an algebraic object that represents a point with multiplicity.
So it's like a point that has been thickened or smeared out in a certain way?
That's a good way to visualize it. And in this case, the fat point actually corresponds to a line that's part of the surface, but wasn't part of the original curve that generated the surface.
So again, the Chow Lam recovery is picking up on this hidden line that wasn't explicitly part of the original construction.
Exactly. And it highlights the fact that the recovered variety might not always be a smooth, well-behaved object. It can have singularities or other unusual features that reflect the complexities of the Chow Lam form.
It's like the recovered variety is telling us, hey, there's more to this shape than meets the eye.
Precisely. Now, moving on to another fascinating class of examples, Pratt and Ranestad explore what happens with multi-ruled varieties.
Multi-ruled varieties are those that can be generated by sweeping multiple families of linear spaces through space, right?
That's right. It's like taking multiple sets of lines and using them to weave the surface.
And this multi-ruled structure can lead to some surprising behavior in the Chow Lam recovery, can't it?
It can. They find that with these multi-ruled varieties, you can actually have different varieties that share the same Chow Lam form.
So it's like different objects casting the same shadow.
Exactly. And this raises some fundamental questions about the uniqueness of the Chow Lam recovery.
It means we can't just assume that the recovered variety is the one and only solution.
Right. We have to be mindful of the fact that there might be other varieties that fit the data equally well.
And to illustrate this phenomenon, Pratt and Ranestad analyze a specific embedding called the Segre embedding.
The Segre embedding is a way of combining two or more projective spaces into a higher dimensional projective space.
It's like taking multiple sheets of paper and weaving them together to create a more complex surface.
That's a good analogy. And what they show is that you can use the Segre embedding to construct different varieties that have the exact same Chow Lam form.
So different weaving patterns can result in the same overall shape, at least as far as the Chow Lam form is concerned.
Precisely. And they extend this analysis to multi-Segre varieties, which involve more than two factors, and find that this phenomenon of multiple varieties sharing the same Chow Lam form persists in higher dimensions.
So it's a recurring theme in the Chow Lam recovery process.
It seems to be. And it underscores the importance of understanding the specific context and the way the variety is constructed when interpreting the results of the recovery.
We can't just blindly trust the output of the Chow Lam form.
We have to be aware of its limitations and the possibility of ambiguity in the reconstruction process.
This is all very insightful. Now I'm curious about another class of examples they mentioned. Linear determinantal hypersurfaces.
Linear determinantal hypersurfaces are a fascinating class of geometric objects. They're hypersurfaces, meaning they're defined by a single equation, but that equation comes from the determinant of a matrix.
So it's like we're taking a matrix, calculating its determinant, and setting it equal to 0, and that defines our hypersurface.
Exactly. And what makes them particularly interesting is that they're ruled by two families of linear spaces.
So we can sweep two different families of lines or planes through space to generate the entire hypersurface.
That's right. And Pratt and Ranestad discovered that this ruled structure has a direct impact on the Chow Lam recovery.
How so?
They show that these two rulings actually lead to two pairs of varieties that share the same Chow Lam form.
So the Chow Lam form sees these two pairs as essentially equivalent, even though they come from different geometric origins.
Exactly. One pair consists of the original hypersurface and its dual variety, and the other pair corresponds to the two families of linear spaces that rule the hypersurface.
And like the Chow Lam form is highlighting a kind of duality within these objects.
It is. And to make this even more concrete, Pratt and Ranestad connect this analysis to a classic example, the cubic surface.
A cubic surface is a surface in three-dimensional projective space that's defined by a cubic equation.
Exactly. And they show that a cubic surface can be viewed as a special case of a linear determinantal hypersurface.
So there's a hidden connection between these two objects.
There is, and it gets even more fascinating. They connect the Chow Lam recovery for a cubic surface to a special configuration of lines on the surface called a double six.
A double six, what's that?
It's a collection of 12 lines on the cubic surface that are arranged in the specific pattern. You can divide them into two groups of 6, and no two lines within the same group intersect.
But each line from one group intersects 5 lines from the other group.
Precisely. It's a very elegant and symmetrical configuration. And Pratt and Ranestad demonstrate how this double six structure emerges naturally when you analyze the Chow Lam recovery for a cubic surface.
So the Chow Lam form is picking up on this subtle geometric arrangement.
It is. It's a beautiful example of how seemingly abstract algebraic concepts can be reflected in concrete geometric features.
Now, moving beyond these specific examples, Pratt and Ranestad address a more general question. Do generic linear sections of Grassmannians always have residual components in their Chow Lam recovery?
Essentially, they're asking, if we take a random slice through a Grassmannian, will the Chow Lam form always give us back that slice perfectly, or will there be extra pieces?
It's a question about the general behavior of the Chow Lam recovery.
Exactly. And it's a challenging question to answer in full generality. But Pratt and Ranestad provide some valuable insights by looking at specific cases involving curves and threefolds.
What do they find?
For curves, they prove that if the curve comes from intersecting GR2n with a generic linear space of the appropriate dimension, the Chow Lam recovery is perfect except when n equals 4.
Why the exception for n equals 4?
In that specific case, the curve is rational, meaning it can be parameterized by a single variable, and that introduces an extra line in the recovered variety.
Ah, so the rationality of the curve causes the Chow Lam recovery to be imperfect in that case.
Exactly. But for threefolds, they analyze a specific scenario where the threefold is obtained by intersecting GR25 with 3 generic hyperplanes.
And in this case, they prove that the Chow Lam recovery is indeed perfect.
Yes. They use the geometry of Fano threefolds and some clever dimension arguments to show that there are no extra components in this scenario.
So the Chow Lam recovery behaves differently depending on the specific type of threefold we're considering.
It does. And based on these examples, Pratt and Ranestad formulate a bold conjecture. They propose that for generic linear sections of Grassmannians, the Chow Lam recovery is always perfect.
So they're suggesting that those extra components we've been discussing aren't a generic phenomenon, but rather something tied to specific structures or properties of the varieties.
Exactly. If this conjecture is true, it would be a significant result.
It would tell us that those extra components aren't an inherent limitation of the Chow Lam form itself, but rather a reflection of something special about certain varieties.
That's right. And it would underscore the importance of understanding those special characteristics if we want to fully grasp the intricacies of Chow Lam recovery.
Well, it's been an incredible journey exploring the world of Chow Lam recovery with you.
I've enjoyed it immensely. It's fascinating to see how a seemingly simple question about reconstructing a shape from its shadows can lead to such deep and intricate mathematical concepts.
And how those concepts can even connect to areas like theoretical physics.
It's a reminder of the power and interconnectedness of mathematical ideas.
And the endless possibilities for discovery that lie ahead.
Absolutely. So until next time, keep exploring the fascinating world of mathematics.
And keep diving deep. Okay, we're diving deep today into a paper titled Chow Lam Recovery.
By Elizabeth Pratt and Kristian Ranestad.
Right.
All about subvarieties of the Grassmannian.
Ooh, the Grassmannian. Sounds complicated.
Well, think of it as the space that holds all possible lines, planes and higher dimensional spaces
Okay.
within a given projective space.
I see. So kind of like a catalog of all these different spaces.
Yeah, and we're looking at specific shapes, these subvarieties, living within that space.
So it's like we have this giant library of spaces.
Yeah.
And we're zooming in on some particularly interesting ones.
Exactly. And what's fascinating is this paper explores whether we can reconstruct these shapes perfectly.
Perfectly.
Just by looking at their shadows or projections.
Projections. I'm intrigued. Tell me more.
Imagine shining a light on a 3D object and looking at the shadow it casts on a flat surface.
Okay, I could picture that.
It's like trying to figure out the exact shape of that 3D object just from its 2D shadow.
Ah, so we're trying to reconstruct the whole thing just from limited information.
Precisely. And the authors use this intriguing concept called the Chow Lam form.
Okay, break that down for me. What is this Chow Lam form?
It's essentially an equation that encodes all the information about these projections.
So it's like a mathematical blueprint of all the possible shadows.
That's a good way to think about it, but here's the catch. Unlike with regular shapes in projective space,
Uh-oh, what's the catch?
it turns out you can't always perfectly reconstruct a subvariety just from its Chow Lam form.
Wait, so even with this blueprint, we might not get the original shape back?
That's right, and that's what makes this paper so interesting.
Okay, I'm hooked. So where do we start with all this?
Let's break it down.
Okay.
First, let's revisit the Grassmannian, denoted as Gr, KMN.
Okay, remind us what that represents again.
It represents the space of all K1-dimensional subspaces.
Subspaces.
Yeah, of a projective space denoted by Pn1.
Okay, that's a mouthful. Can you give us an example?
Sure, like GR24 represents all the lines in a three-dimensional projective space.
So each point in the Grassmannian is actually a whole line.
Precisely. Now let's talk about these projections.
All right, how do they work in this context?
So we have these linear projections between Grassmannians. We denote them by Z.
Z for projection, got it.
And they essentially map our original space, Grass KAN, to a potentially smaller Grassmannian, Grass AR.
So we're shrinking the space, kind of like zooming out.
In a way, yeah. And this is where that shadow analogy comes in.
Okay, I'm picturing the shadow again. Go on.
Imagine you have a subvariety, let's call it V, inside the Grassmannian.
Okay, so V is our shape.
Right, and when we apply this projection Z to V, we get ZV, which is like the shadow of V in this smaller Grassmannian.
So ZG is the shadow, and V is the original object.
Precisely. But things get really interesting when we try to go back from the shadow to the original object.
Meaning we want to reconstruct V just from knowing its shadow.
Exactly, and the paper dives into whether that's even possible.
Using this Chow Lam form. Okay, so to recap, we have this projection Z, which takes us from V to its shadow Z.
Right.
And we're trying to figure out if we can go back from ZV.
Using the information encoded in the Chow Lam form.
Now remember the paper using some notation like Z1, ZV?
Ah, yes, good catch.
Can you explain that a bit more?
So Z1, ZV represents all the points in the original Grassmannian.
The bigger space.
Right, that project down to ZV under the projection Z.
So it's like everything that could potentially cast that particular shadow.
Precisely.
Okay, so we have ZZV and Z1ZV.
Now, let's get to the heart of it. The Chow Lam form.
Finally, tell me everything.
The Chow Lam form, denoted by CLV, is an equation, and this equation describes a very specific set.
A set of what?
It's the set of all k-dimensional linear spaces
Okay.
that intersect our subvariety V in at least a point.
So it's like a collection of all the spaces that touch our shape V in some way?
Precisely. Think of it as capturing all the possible shadow positions of V under these projections.
So the Chow Lam form is like a record of all the possible shadows V could cast.
That's a great way to put it.
Now, you mentioned earlier that reconstructing V isn't always possible, even with the Chow Lam form.
Right.
How does that play out?
Well, the paper defines something called the recovered variety,
Recovered variety.
denoted by WV, and it's the set of all L points in the Grassmannian that satisfy the conditions imposed by the Chow Lam form.
So it's like we take the Chow Lam form and use it to build a new shape, WV.
Exactly, and here's the thing.
What's the thing?
This WV isn't always equal to our original variety V.
Wait, so even with all that information from the Chow Lam form, we might end up with a different shape.
That's right, there might be additional points or even entire components that weren't part of V.
So it's like the shadow is tricking us, making us see something that's not really there in the original object.
It's not quite tricking us.
Okay.
It's more like the shadow doesn't contain all the information needed to perfectly reconstruct the original object.
I see. So it's like trying to build a puzzle, but some pieces are missing?
And this is a key difference from the classical Chow form,
The classical Chow form.
which is used for projective varieties, not subvarieties of the Grassmannian.
Okay, so the classical Chow form gives you perfect reconstruction, but this Chow Lam form doesn't always.
Exactly. And that's what this paper is all about.
Figuring out when it works and when it doesn't.
Precisely.
All right, so how do we actually calculate all of this?
The Chow Lam form and the recovered variety.
Yeah, it seems like there's a lot of complex math involved.
There is, but the authors use a clever trick with something called Plucker coordinates.
Plucker coordinates. Remind me what those are again?
They're a way to represent points in the Grassmannian with coordinates, kind of like giving each point an address.
So we're giving coordinates to these lines, planes, and higher dimensional spaces.
Exactly.
Okay. And how do they use these coordinates to find the Chow Lam form?
Well, they start by representing the relationship between a k-dimensional linear space P
Okay.
and a larger linear space Q.
Which contains P.
Right, they represent this relationship using an incidence variety, which we'll call OR.
So R captures how P sits inside Q.
Precisely. Then they intersect this A with the equations defining our subvariety V.
So we're focusing on the part of A that's relevant to our shape V.
Exactly. And finally, they project this intersection, and this projection gives us the Chow Lam form.
So it's like we're filtering all possible space arrangements based on the equations of V and then condensing that information into the Chow Lam form.
Precisely. And to compute the recovered variety, they expand the dual Plucker coordinates of the join of spaces A and P.
Dual Plucker coordinates. Join of spaces. Hold on, let's unpack that.
So dual Plucker coordinates are another way to represent points in the Grassmannian.
Different from the regular Plucker coordinates we talked about earlier.
Yeah, they're related, but they use complementary indices.
Okay, and what's this join of spaces?
It's a way to combine two spaces, A and P, into a larger space that contains both of them.
I see. So we're taking these two spaces and merging them together in a specific way?
Exactly, and the key is that when this join lies in the Chow Lam locus.
Meaning it satisfies the conditions of the Chow Lam form.
Right, we get these polynomial equations in the dual Plucker coordinates of P.
Right.
And these equations actually define our recovered variety, WV.
Wow. So it's a lot of algebraic manipulation with these coordinates, but it ultimately gives you a way to describe both the Chow Lam form and the recovered variety.
Precisely. And the best part is they even provide concrete examples in the paper.
Examples. That would be helpful to see how this all works in practice.
For instance, example 2.2 shows how even for a smooth curve in projective space,
So a nice simple shape.
the recovered scheme can contain extra components.
Hold on, what's the difference between a scheme and a variety? You said scheme with emphasis.
Ah, yes. You're sharp.
Well, I try.
So think of a variety as the geometric object itself, the shape,
Okay.
defined by its equations.
I see.
The scheme is a bit more sophisticated.
Sophisticated how?
It includes additional information about the multiplicity of points,
Multiplicity.
like how many times a point is counted in the solution.
That sounds abstract.
It is, but the key is that even if a variety looks smooth, geometrically, its corresponding scheme might reveal some hidden complexity.
So the scheme is giving us a deeper view into the structure of the variety.
Exactly.
But to keep things simple, the paper focuses mainly on the recovered variety as an algebraic set.
Right, that's enough to get the main ideas across.
So we're not diving too deep into the scheme stuff.
Not in this paper at least, but it's an interesting area for further exploration.
Okay, noted. But I'm still curious. Can this recovered variety, WV, be significantly different from the original V? Like much larger?
Yes, absolutely. And they have an example to illustrate this, example 2.4.
What kind of example?
They use a Schubert variety.
Schubert variety. Another new term.
It's just a specific type of subvariety in the Grassmannian.
Okay, but what's special about it in this context?
They show that for this Schubert variety, the recovered variety, WV can be arbitrarily larger than the original V.
Arbitrarily larger.
Meaning the difference in their size, measured by something called codimension, can be as big as you want.
So there's a real possibility of losing a lot of information when we're working with this Chow Lam form.
That's right, and that's what motivates the next part of the paper.
Which is?
They start investigating when this recovery is possible, under what conditions we can get V back perfectly.
So it's like a detective story trying to find the clues that lead to perfect reconstruction.
And a key tool in this investigation is Theorem 3.2.
Theorem 3.2 sounds important.
It is. It provides a necessary condition for a point to belong to the recovered variety.
So it's a test to see if a point is potentially part of our reconstructed shape.
Exactly.
Okay, I'm ready for the details. How does it work?
It's based on a dimension argument, kind of like checking if things fit in the right dimensions.
I'm intrigued. Go on.
So if a point P is in our recovered variety, WV,
Okay.
then any linear space Q containing P,
So a larger space that encompasses P.
right, that Q must also intersect our original variety, V.
So there's some overlap between Q and V.
Precisely. And they divide V into these subsets,
Subsets?
denoted VPI, based on the dimension of the intersection between spaces in V and P.
So they're grouping points in V based on how much they overlap with P.
Exactly. And the theorem says that for P to be in the recovered variety, WV,
Sure.
at least one of these subsets, VPI, must have a dimension greater than or equal to a specific value.
A specific value.
It's a bit technical, but essentially it means there needs to be enough overlap between P and V for the recovery to work.
I see. So it's like checking if there's enough information in the shadow to reconstruct that particular point.
That's a good way to think about it.
Now, this condition in Theorem 3.2, is it enough to guarantee that the point is in the recovered variety?
That's the question, isn't it? Unfortunately, no.
Oh, no. So it's not a foolproof test.
They actually provide a counterexample in example 3.3.
A counterexample.
Where a point satisfies the dimension condition, but it's not in the recovered variety.
So it passes the test, but still fails to be part of the reconstructed shape.
Exactly.
So this Chow Lam recovery is trickier than just checking dimensions. There's more to the story.
Absolutely. There are subtle geometric factors at play as well.
Okay, now I'm really interested in those geometric aspects.
Well, let's delve into them then.
I'm ready. So the next section of the paper delves into this connection with dual varieties.
Ah, yes. The dual perspective.
Can you remind us what a dual variety is in this context?
So in projective geometry,
Okay.
a dual variety represents a variety in terms of its tangent spaces.
Tangent spaces.
You can think of them as the linear spaces that just touch the variety at a given point.
Okay, so it's like describing this shape from the perspective of all these tangent spaces.
Exactly. For instance, the dual of a surface in projective space
Okay.
would consist of all the hyperplanes,
Hyperplane.
which are like n1-dimensional spaces in an n-dimensional projective space
Okay.
that are tangent to that surface.
So it's like looking at the shape from the outside in, using all these tangent hyperplanes to define it.
It's like an inside-out perspective, yeah.
So how does this relate to the Chow Lam locus?
Well, proposition 4.1 in the paper establishes a key connection.
Okay, tell me more.
It states that the dual variety of our original variety, V, is always contained within the Chow Lam locus.
Meaning the dual variety is a subset of the Chow Lam locus.
Precisely. And furthermore,
That's more
if
fun.
their dimensions match,
Meaning the dual variety and the Chow Lam locus have the same dimension.
right, then they're actually equal.
So in those cases, the Chow Lam form has a direct geometric interpretation in terms of these tangent spaces.
Exactly. It's telling us something fundamental about the geometry of our shape.
That's pretty elegant, and I imagine this leads to some interesting consequences.
It does. For example, it provides a nice criterion for when a space belongs to the recovered variety.
Oh, so it helps us determine if a point is part of the reconstructed shape.
Precisely. The proposition states that a K1-dimensional linear space P belongs to our recovered variety WV,
Right.
if and only if its dual space,
The dual of P.
right, is contained within the dual variety of V.
So if the dual of P is embraced by the dual of V, then P itself is in the recovered variety.
That's a good way to visualize it. It's all about duality.
And this dual perspective seems particularly helpful when we're dealing with curves and surfaces in the Grassmannian.
Yes, the latter part of section 4 focuses on those cases.
Okay, now I'm curious about those specific cases.
Well, they start with corollary 4.2.
Which is about
It talks about varieties where the dimension is one less than a prime number.
prime numbers popping up here. That's interesting.
It is. It highlights a special situation.
Okay, tell me more.
It essentially says that for a variety V in Gr, Km,
Our usual setting,
right, if the dimension of the spaces represented by V,
meaning the K1 dimensional spaces.
yes, if that dimension is a prime number minus 1,
Okay.
then its Chow Lam form can only exist if n itself is also a prime number.
So the dimension of the ambient projective space has to be prime as well.
Precisely. It's a constraint imposed by this primality condition.
Fascinating. And what about corollary 4.3? That one focuses on curves in GR2N, right?
Yes, those represent collections of lines in projective space.
So what does it tell us about recovery in this case?
It gives us a very specific condition for when a line belongs to the recovered variety of a curve.
Okay, what's the condition?
It states that for curves in GR2N that generate what we call non-conical surfaces.
Non-conical surface.
It just means the surface isn't a cone.
Okay, so a fairly general type of surface.
Right. For those curves, a line is in the recovered variety WV, if and only if it's entirely contained within the surface generated by the original curve.
So the line has to be fully embedded in that surface. It can't just poke out.
Exactly. It has to live within the surface swept out by the curve.
I see. So we're getting a more refined understanding of the conditions for perfect recovery as we go along.
Absolutely. And things get even more interesting in section 5.
Oh, why is that?
Because they start talking about families of varieties that share the same Chow Lam form.
Wait, so different shapes can have the same Chow Lam form?
That's right. They call these multi-ruled varieties.
Multi-ruled, meaning?
It means they can be swept out by different families of linear spaces.
So it's like multiple different objects casting the same shadow.
Precisely. And this highlights a key point.
What's that?
The Chow Lam form doesn't always capture the full information about the internal structure of the variety.
Meaning it might not tell us everything we need to know to distinguish between different shapes?
Exactly. Corollary 5.1 formalizes this.
Oh, so.
It states that if two varieties in the Grassmannian sweep out the same surface in projective space...
So they trace out the same overall shape.
Right, then they'll have the same Chow Lam locus.
So the shadow is more about the overall surface, not the specific arrangement of spaces that make up the variety.
Precisely. And they illustrate this beautifully with Segre varieties.
Segre varieties.
They're a way to embed the product of projective spaces into a higher dimensional projective space.
Okay, that sounds abstract.
It is. But the key takeaway is that example 5.2 shows that the Sengrium embedding of PK1, x PK1, into PK21.
I'm trying to keep up.
Don't worry too much about the notation.
Okay.
The main point is that this Segre embedding has two natural families of K1 dimensional spaces.
Two different ways to sweep it out.
Exactly. And both families sweep out the same Segre variety, leading to the same Chow Lam locus.
So we have two distinct varieties in the Grassmannian with identical Chow Lam forms because they trace out the same surface?
Precisely. And example 5.3 generalizes this to Segre embeddings with more factors.
More factors meaning?
More projective spaces being multiplied together.
I see. So this phenomenon of multiple varieties sharing the same Chow Lam form is actually quite common.
It is. And it gets even more interesting with linear determinantal hypersurfaces.
Linear determinantal hypersurfaces, another new term.
They're hypersurfaces defined by the vanishing of determinants of matrices.
Matrices.
Yes, but the entries of these matrices are linear forms.
Okay, getting a bit technical here.
The key point is that these hypersurfaces are also multi-ruled.
Meaning they can be swept out by different families of linear spaces?
Exactly. Just like the Segre varieties.
So they can also lead to multiple varieties with the same Chow Lam form.
Precisely. And example 5.4 dives into a specific determinantal hypersurface denoted SIC, which lives in PK21. And it turns out that carefully chosen linear sections of SIC,
Linear sections.
meaning we intersect SIC with a linear space.
I see.
These linear sections can share the same Chow Lam form as the projected Segre variety.
So again, we have different shapes casting the same shadow.
Exactly. It's like a theme in this section.
Now, you mentioned a concrete example using a cubic surface, right?
Yes. They start with a 3x3 matrix M, whose entries are linear forms in 6 variables.
6 variables. That's a lot.
It is, but bear with me.
Okay, I'm listening.
The determinant of this matrix, M.
The determinant, so we're calculating a single number from this matrix.
Precisely. And that number defines a cubic surface, denoted S, in P5.
So even though we're in a higher dimensional space, we still get a cubic surface.
Exactly. The determinant carves out this specific surface within that higher dimensional space.
That's pretty cool. And what's special about this cubic surface?
The beauty is that this surface, S, is ruled by 2 families of planes.
2 families of planes, meaning?
There are 2 different ways to sweep out the surface using planes.
Okay, I'm picturing it.
These families are denoted V1 and V2.
V1 and V2, got it.
And they arise from setting linear combinations of rows or columns of our matrix M to 0.
So the matrix is encoding the information about these planes.
Precisely.
And we can think of these planes as points in the Grassmannian, GR36.
Exactly. Each plane corresponds to a point in that Grassmannian.
So we have 2 varieties in the Grassmannian, both tracing out the same cubic surface.
And therefore sharing the same Chow Lam form.
It's like that Segre variety example all over again.
It is. It reinforces the idea that the Chow Lam form doesn't always distinguish between different varieties.
But they take it even further with this cubic surface example, right? They connect it to something called a double six.
Ah, yes, the double six, a classic gem in the geometry of cubic surfaces.
Okay, I need you to break this down for me. What is a double six?
So a double six consists of two sets of six lines.
Six lines, okay.
On the cubic surface, but they have a very special intersection pattern.
A special intersection pattern, meaning...
No two lines within the same set intersect.
Okay, so they're all parallel or skewed to each other.
Right, and each line from one set intersects exactly 5 lines from the other set.
So it's like a very intricate arrangement of these lines on the surface.
It is a beautiful interplay between algebra and geometry.
Now, how do they get to this double six from our matrix M and the cubic surface?
They use a clever construction involving a pencil of hyperplanes in P5.
A pencil of hyperplanes, what's that?
It's a one-parameter family of hyperplanes.
A family of hyperplanes, so infinitely many of them.
Exactly. But they all pass through a common three-dimensional space, which they denote by L.
So it's like a stack of hyperplanes, all pivoting around this common space.
L. That's a good visualization.
And how does this pencil help us find the double six?
Well, the intersection points of the dual variety of S.
So the dual of our cubic surface.
Right, the intersection points of that dual variety with the dual of L.
Okay, getting a bit abstract here.
Just keep in mind that these intersection points correspond to planes in S.
Planes in our cubic surface.
Yes, but these planes have a special property.
What property?
They meet L in a line.
So each of these planes slices through L along a line.
Precisely. And by restricting our cubic surface S to this three-dimensional space L.
Meaning we're zooming in on the part of S that lives inside L.
Exactly. We get a new cubic surface, denoted SL.
SL, the restricted cubic surface.
Right, and this new surface lives inside L, which is a P3.
So we've gone from a cubic surface in P5 to a cubic surface in P3.
Precisely. And now comes the magic.
I'm ready for the magic.
They analyze the determinant of a 3x3 matrix.
Another matrix.
Yes, but this one is constructed from M restricted to L.
So we're taking our original matrix M and zooming in on the part that corresponds to L.
Exactly. And the key is that the points where this determinant vanishes.
Meaning the determinant equals 0.
Right. Those points correspond to planes in S that meet L in a line.
Just like the planes we were talking about earlier.
Precisely. It all ties together beautifully.
Okay, but how do we find the actual lines of the double six?
They use something called Porteus's formula to calculate the degree of this locus.
The degree of the locus, meaning?
Number of points where the determinant vanishes, counting multiplicity.
Okay.
And it turns out that this degree is 6.
Ah, there's our 6.
Exactly. But we need 2 sets of 6 lines for a double 6.
Right. We only have 1 set so far.
And this is where the duality between rows and columns of our matrix comes in.
Okay, how does that work?
They take the tensor representing our matrix M.
A tensor is just a generalization of a matrix, right?
Right, and they multiply it by the matrix representing L.
Okay.
But they do this multiplication in 2 different ways.
2 different ways.
First, they multiply on one side, which gives them 6 lines corresponding to what they call generalized rows.
Generalized rows, okay.
And then they multiply on the other side, which gives them another 6 lines corresponding to generalized columns.
So the side we multiply on determines whether we get rows or columns.
Precisely. And these 2 sets of 6 lines...
3 from the rows and 3 from the columns.
6 from the rows and 6 from the columns, actually.
Oh, right, 6 and 6.
Those form our double 6.
Wow, that's a pretty intricate construction, but it's amazing how it all comes together.
It is. It's a beautiful illustration of the power of algebraic geometry.
This cubic surface example is really mind-blowing.
It is, isn't it? It shows how seemingly simple geometric objects
like a cubic surface
can harbor such incredible mathematical depth.
Absolutely. So what's next in our Chow Lam journey?
Let's move on to something even more fascinating. Schubert arrangements.
Schubert arrangements. Sounds intriguing.
They take us even deeper into the world of Schubert calculus.
I'm ready to dive in. Okay, Schubert arrangements. Those sound like they're taking us even deeper into this Schubert calculus territory.
They do. They're a specific class of subvarieties in the Grassmannian formed by intersecting the Grassmannian with special divisors.
Divisors?
Yeah, called Schubert divisors.
Okay, so we're getting even more specific with the types of shapes we're looking at.
Precisely. And remember that Schubert varieties, in general, are defined by imposing conditions on how spaces in the Grassmannian intersect with a fixed flag of linear spaces.
Right, so we're looking at very particular configurations of those linear spaces.
Exactly.
So what did they discover about Chow Lam recovery for these Schubert arrangements?
Well, a key finding is that for certain types of Schubert arrangements,
Okay.
the recovered variety,
I'll
like the
believe
V,
a reconstructed shape, right?
right, often contains extra components that weren't present in the original variety V.
So even with these neatly organized Schubert varieties, we still have this issue of extra stuff appearing in the recovery.
We do, and they call these recovered Schubert components.
Recovered Schubert components.
Yeah.
Okay. So what kinds of extra components pop up?
They explore this through several examples and introduce some notation to help keep track of everything.
Notation is always good. What kind of notation?
Well, first they use A to represent a specific type of Schubert variety, where
Okay.
A is a partition, like a way to break down a number into smaller numbers.
Right. Like 5 can be written as 2 plus 3 or 1 plus 4. Those are partitions.
Exactly. But here, the partition has to fit into a KX and K box.
A box.
It's a way to visualize the constraints on the partition, but we don't need to go into the details here.
Okay, fair enough. So A represents a specific Schubert variety based on this partition.
Precisely. Now, they also use a shorthand notation to represent the partition itself.
Oh, that's helpful. What's the shorthand?
They write it as 1 ball of J, a lot of 1 of it.
Lots of symbols.
Don't worry too much about the specifics.
Okay.
The main idea is that A represents the number of parts of size J in the partition.
Okay, so like if we had the partition 332222220, that would be written as 3224.
Exactly. Because we have 2 parts of size 3 and 4 parts of size 2.
Okay, so that shorthand helps to compactly describe the partition.
It does. Now let's get back to those recovered components.
Right. What kinds of components appear in these Schubert arrangements?
Well, example 6.1 looks at a specific threefold, V equals A31.
A31, so that's our Schubert variety.
Right, and it represents the set of lines in P4 that intersect 3 generically chosen planes.
So we have 3 planes floating around in this 4-dimensional projective space.
Exactly, and we're looking at all the lines that pierce through all 3 of them.
Okay, so what does the recovered variety look like for this A31?
They show that the recovered variety WV, besides containing V itself,
So it at least captures the original shape.
it does, but it also has 3 extra components of each of 2 types, A3 and A22.
So 6 extra components in total.
That's right, and it's important to understand what these components represent geometrically.
Okay, what do they represent?
The components of type A3 consist of lines that intersect the intersection of 2 of the chosen planes, denoted high A, HJ.
So like if we have planes H1, H2, and H3, a line in this A3 component would have to pass through the intersection of H1 and H2.
Exactly, it has to hit that specific line where the 2 planes meet.
Okay, what about the A22 components?
Those are even simpler. They consist of lines that are entirely contained within one of the chosen planes.
So a line that just lies flat within one of the planes.
Precisely.
So to summarize, the first type captures lines passing through the intersection of 2 planes, and the second type captures lines lying within a single plane.
Exactly, and they provide a nice geometric argument to explain why these extra components appear.
Oh, I like geometric arguments. Tell me more.
They consider a generic plane, Q, and how the chosen planes, H1, H2, and H3, intersect with this plane Q.
Okay, so we have this 4th plane Q entering the picture.
Right, and for a generic Q, the chosen planes will intersect it in 3 points.
3 points, 1 from each of the chosen planes.
Exactly, but the key is that these 3 points generally don't have what we call a common transversal.
A common transversal.
It just means a line that intersects all 3 points.
Oh, so there's generally no single line that threads through all 3 intersection points.
Precisely. But if we choose Q strategically,
Strategically how?
if we choose it to contain a line L from one of the recovered components, then a common transversal must exist.
So by placing Q carefully, we force the existence of a line that hits all 3 points.
Exactly. And this explains why those equal components appear.
Okay, I'm following. But how does this work for each type of component, A3 and A22?
Well, for type E3, where L meets H1A, H2,
So L passes through the intersection of those 2 planes.
right, then the line connecting this intersection point with the 3rd point on Q.
The point where H3 intersects Q.
Exactly. That line acts as our common transversal.
I see. So the transversal is formed by connecting the intersection point to the 3rd point.
Precisely. And for type A22, where L lies within H1,
Okay.
well, H1 itself intersects Q in a line.
Because they're both planes.
Right, and that line of intersection acts as the transversal.
So in this case, the transversal is already there because L lies within H1.
Exactly. And what's cool is that this argument works regardless of the dimension of the ambient projective space.
Meaning it doesn't matter if we're in P4 or P5 or even higher dimensions.
Right. Those recovered components persist for V for A31 euro to N for any A05.
So it's a general phenomenon, not just specific to P4.
Exactly. Example 6.2 provides another illustration with A71 euro to A, which represents lines meeting 7 generic hyperplanes.
7 hyperplanes, so we're in an even higher dimensional space now.
We are, but the same principle applies. This time we get recovered components of types A62 and A7.
So more hyperplanes lead to even more types of recovered components.
It seems that way. And notice how the type of component reflects how lines intersect those hyperplanes.
Right, like A62 means the lines intersect 6 of the hyperplanes in a specific way and are contained within the 7th.
Precisely. It's all about those intersection patterns.
Now, they do mention a limit on the dimension n for these components to exist, right?
Yes. N needs to be large enough to accommodate the geometry.
Meaning?
Well, for A62, for example, N needs to be at least 8.
Why 8?
Because the intersection of 3 hyperplanes in P7 is just a point.
Okay.
But we need that intersection to contain lines for the A62 component to make sense.
So we bump up the dimension to P8 so that the intersection of 3 hyperplanes can be a line.
Exactly. And for A7, N needs to be at least 9 for similar reasons.
So there's a minimum dimension for these components to fit inside the space.
Precisely. And Theorem 6.3 generalizes these observations even further.
Okay, how does it generalize them?
It looks at Schubert varieties of the form Ecke plus 11 euro, co, N.
So a more general form than just A31 or A71.
Exactly. And it states that for fixed K and IK,
Okay.
and for NKI plus 1 plus 1.
So again, n needs to be large enough.
Right. The recovered variety WV always contains recovered components of types Ecke plus 1 plus 2, 2, and so on, up to AKK plus 1 plus KK.
Wow, that's a lot of components. But it seems like there's a pattern based on K and I.
There is. It's a beautiful combinatorial pattern.
And how do they prove this theorem?
They use a similar geometric argument as before with the transversal.
So they extend that argument to this more general setting.
Precisely. They consider a generic space Q in the Chow Lam locus and show that if Q contains a K1 space from one of those predicted recovered components, then it guarantees a common transversal to the chosen hyperplanes.
So the transversal argument still holds the key.
It does, but they do acknowledge that there might be other recovered components not covered by this theorem.
Oh, so it's not the whole story.
Not necessarily. For example, they found A2 to A3 appearing in the recovered locus of A51 GR27.
So there are exceptions to the pattern.
There might be, but they propose in conjecture 6.4 that for large GI, the components described in the theorem might be the only ones.
So the pattern might hold more generally for larger values of I.
That's the conjecture.
Okay, so lots to explore there. Now, what happens when we move beyond these specific Schubert arrangements? What about more general linear sections of the Grassmannian?
That's a great question, and it turns out to be much harder to answer.
Harder how?
Well, they mention that it's a difficult question to study systematically.
So we don't have nice, clean theorems like for the Schubert arrangements.
Not yet, at least. But they do look at some specific examples of curves where the recovered variety matches the original.
So perfect recovery is possible in some cases.
It is, and Proposition 6.5 dives into a specific threefold example.
What kind of threefold?
It's the intersection of GR2 through 5 with a three-dimensional linear space.
Okay, so a specific way to slice the Grassmannian.
Right, and they prove that there are no extra components in the recovered variety for this example.
So perfect recovery.
Exactly. And this leads to conjecture 6.6, which suggests that this might hold more generally for generic linear sections.
Generic meaning most linear sections.
Precisely. So there's hope for perfect recovery in more general situations, but more research is needed.
Makes sense. And to wrap things up, they circle back to those positoroid varieties, right?
They do. Remember, those are those special subvarieties connected to the positive Grassmannian.
Right, the positive Grassmannian, which has connections to all sorts of cool stuff like particle physics.
Exactly. And they point out that some of the examples from Theorem 6.3...
The ones with those extra recovered components.
Right, those examples actually include certain positoroid varieties.
So even in the world of positoroid varieties, this Chow Lam recovery can be tricky.
It can. And Corollary 6.7 demonstrates this explicitly with a specific positoroid variety in GR2 area N, where the recovered variety is strictly larger than the original.
So the shadow is deceiving us again, showing us more than is really there.
Precisely. And the paper concludes by emphasizing that systematically studying the Chow Lam recovery of these positroid varieties would be a fruitful direction for future research.
So much more to explore.
Absolutely. This paper opens up a whole new avenue of investigation in this area.
Well, this has been an incredible deep dive into the world of Chow Lam recovery. We've covered a lot of ground, from the basics of the Grassmannian to these intricate Schubert arrangements and positroid varieties.
It's been a wild ride through the geometry of these shapes and their shadows.
And we've seen how this seemingly simple idea of reconstructing a shape from its projections can lead to some really deep and surprising mathematical results.
It's a testament to the power of algebraic geometry and the beauty of these abstract structures.
Absolutely. So to our listeners, if you're interested in exploring the hidden depths of the Grassmannian and the mysteries of Chow Lam recovery, this paper is a great place to start.
And who knows what other fascinating discoveries await in this rich and unexplored territory.
A perfect note to end on. Thanks for joining us on this deep dive into the world of Chow Lam recovery.
It's been a pleasure.
Until next time, keep exploring the fascinating world of mathematics. All right, let's jump right in, shall we? Today, we're diving deep into a fascinating topic that's really at the heart of algebraic geometry.
We're talking about Chow Lam recovery.
Exactly.
Yeah.
So, for those who might be tuning in for the first time, maybe you're not as familiar with this area.
It might sound a bit intimidating at first.
It can,
Mm-hmm.
but it's really all about how we can take geometric objects, these things called varieties, and reconstruct them, like putting together a puzzle.
Think of it like trying to figure out the shape of a 3D object just by looking at its shadow.
Oh, that's a great analogy. So, before we get lost in the weeds here, maybe we should take a step back and talk about what a Grassmannian is, right?
Mm.
Because that's the space where all of this is happening.
Sure. So think of a Grassmannian as a way to organize all the linear subspaces, like lines, planes, those sorts of things.
Okay, so it's like a giant catalog of all these subspaces.
Yeah, exactly. And each entry in this catalog corresponds to a specific subspace.
So, for example, GR24 is it's like the space of all lines in a 3D space.
Precisely. That's a great example.
Okay, cool. Now, what about these projections? How do we actually project a variety from one Grassmannian to another? And what does that even look like?
Well, it's kind of like, how when you shine a light on an object, it casts a shadow? We're doing something similar here.
Okay, so we're basically like flattening the variety by projecting it onto a lower dimensional space.
Yeah, you could say that. And mathematically, these projections, they're actually represented by matrix multiplications.
Matrix multiplications. Okay, that makes sense. But here's the big question, right?
The million-dollar question. Can we go back?
Can we actually reconstruct the original variety just by looking at its projection?
Right.
Like, can we reverse this shadow analogy?
That is the heart of Chow Lam recovery. It's like trying to rebuild the 3D object just from its shadow.
And is that always possible? Can we always do that?
That's where things get really interesting. In a simpler setting, like projective space, we have this thing called the Chow form. It's like a magic polynomial that encodes all the information about the variety.
So using the Chow form, we can perfectly reconstruct the variety from its projections.
Exactly. But when we move to Grassmannians, things get trickier.
Why is that? What makes it different in the Grassmannian setting?
Well, one key difference is that the projections in a Grassmannian, they usually form what we call a hypersurface. It's like a shape of one dimension less.
Okay, so like a curve in a plane or a surface in 3D space.
Exactly. And this hypersurface, we can describe it with a single equation, and that's what we call the Chow Lam form. It's kind of like the Chow form's counterpart in the Grassmannian world.
So it's like the fingerprint of the projected variety.
You got it.
But does this fingerprint always tell us everything we need to know to reconstruct the original variety?
That's the real question, isn't it? And unfortunately, the answer is not always. We can use the Chow Lam form to define something called the recovered variety. It's like the best we can do in terms of reconstructing the original based on the information we have.
So sometimes we get the full picture, and sometimes
we're left with some missing pieces.
Okay, can you give me an example of when this recovery doesn't quite work out, where the recovered variety is different from the original?
Absolutely. There's this classic example in the source material, example 1.4. 4, I believe. It involves this surface called a ruled quadric surface.
Ruled quadric surface. Okay, so what's so special about this surface?
Well, it's a surface in 3D space, and the interesting thing is that it can be covered by two families of lines. Like, imagine taking a piece of string and stretching it tight across the surface. You can move it around, keep it tight, and it traces out a line.
I see, I see. So this surface has two distinct families of lines like that. Okay, so how does this quadric surface connect with the Chow Lam form and recovery?
Well, each of these families of lines, they form a curve in the Grassmannian Gr too. And here's the kicker. Both of these curves, even though they represent different families of lines, they share the same Chow Lam locus.
So they have the same fingerprint, so to speak.
Exactly. And that means that we can't distinguish between them just by looking at their Chow Lam forms.
So it's like two different objects casting the same shadow?
Precisely. And that's why perfect recovery isn't always guaranteed in the Grassmannian setting.
That's really fascinating. It shows how complex this whole recovery process can be. Now, we've talked about Plucker coordinates before. Can you remind me, how do we actually compute this Chow Lam form?
Right. So Plucker coordinates, they give us a way to label each point in the Grassmannian uniquely. It's like a special coordinate system for these spaces. And to compute the Chow Lam form, we use both primal and dual Plucker coordinates.
Okay. And what do these primal and dual coordinates represent?
They basically describe the relationship between a K1 plane and a NR plus K1 plane that contains it. It's a bit technical, but essentially we're using these coordinates to capture the geometry of these planes.
Okay, so we're using these Plucker coordinates to describe the relationship between these planes, and somehow from that, we can get the Chow Lam form.
Exactly. It involves some algebraic manipulations, like eliminating some variables and combining equations. But in the end, we get a single equation that describes the Chow Lam locus.
Okay, so it sounds like a lot of algebraic heavy lifting, but ultimately we get this equation that captures the essence of the variety's projection. But as we've seen, going back from the Chow Lam form to the original variety isn't always straightforward. What are some of the hurdles we might encounter?
Well, one tricky aspect is dealing with singular points. Those are points where the variety is not smooth, like it has a sharp corner or a cusp.
I see. So these singular points can, mess things up.
They can definitely make things more complicated. Even in the simpler setting of projective space, recovering a variety from its Chow form can be tricky at these singular points.
Okay, so it's like having a puzzle piece that doesn't quite fit right.
Yeah, something like that. And with Chow Lam forms, it gets even trickier because even smooth varieties can have these hidden components.
Hidden components, what are those?
They're like extra pieces of the puzzle that we didn't expect to be there. They're not part of the original variety, but they show up in the recovered variety.
So it's like we solve the puzzle, and then we have some pieces left over.
Exactly. And those extra pieces, they can make it difficult to tell what the original variety really looked like.
Wow, it's amazing how complex this seemingly simple idea of recovery can get. Is there any way to, tell for sure when a point belongs to the recovered variety?
Well, there's a helpful criterion in the source material, Theorem 3.2, I believe. It talks about the dimension of the intersection between the original variety and the space spanned by the point in question. It's a bit technical, but it essentially gives us a condition that a point must satisfy to belong to the recovered variety.
So it's like a test we can use.
Yeah, you could think of it that way, but there's a catch.
Oh, no, there's always a catch.
Well, this condition, it's necessary, but it might not be sufficient. Meaning a point might pass the test, but still not actually belong to the recovered variety.
So even with this criterion, we still have to be careful.
Absolutely. There can be subtle geometric reasons why a point might satisfy the criterion, but still not be part of the recovered variety. There's an example in the source material, example 3.3, that illustrates this point.
Okay, so it sounds like we can't just blindly trust the criterion. We need to combine it with other geometric insight.
Exactly. It's all about understanding the geometry and using our intuition to guide our interpretation.
Okay, that makes sense. Are there any cases where the connection between the Chow Lam form and the original variety is more clear-cut, where we can be more confident about the recovery?
There is. When the Chow Lam locus turns out to be what we call the dual variety of the original variety, things become a bit more elegant.
Dual variety. Okay, that's a new term. Can you explain that a bit?
Sure. So you have a variety, right? And at every point on this variety, you can imagine drawing a tangent line or a tangent plane, or in higher dimensions, a tangent hyperplane. It's like a a flat space that just touches the variety at that point.
Okay, so it's like a plane that just grazes the variety without cutting through it.
Yeah, that's a good way to visualize it. And the dual variety is basically the collection of all these tangent hyperplanes. It's like a mirror image of the original variety, but in a different space.
So it's like looking at the variety from a different perspective, through the lens of its tangent hyperplanes.
Precisely.
That's really cool. And you're saying that when the Chow Lam locus is the same as this dual variety, recovery becomes easier.
In some cases, yes. It gives us a more direct link between the Chow Lam form and the original variety.
That's fascinating.
Right.
Are there any specific types of varieties where this duality connection is particularly helpful?
Curves are a great example. If we have a curve in a Grassmannian, and if its Chow Lam form exists, then its Chow Lam locus lives in the dual projective space. So it's like the Chow Lam form is telling us about the dual variety of the curve.
Okay, so we're talking about curves and Grassmannians, and their Chow Lam forms are connected to their dual varieties. Can we see this in action, like in a concrete example?
Sure. Let's consider a curve in GR2N where the curve's image in projective space isn't a cone.
Okay, so we have a curve, but its image isn't a cone.
Right. And Corollary 4.3 tells us that in this case, a line belongs to the recovered variety, if and only if it's contained within a certain surface.
A certain surface. What kind of surface?
It's the surface swept out by the lines of the original curve. Like imagine taking each line in the curve and moving it around. It traces out a surface.
I see. So the lines in the recovered variety have to fit within this surface.
Exactly.
Okay, so it's like a geometric constraint on the recovered variety.
Yeah.
Are there any, like, real-world examples where we can see this duality connection at play?
There's a nice example involving the Hertzebruch surface. It's a surface that we can embed in projective space, and we can look at the curve formed by its rulings, which are families of lines.
Rulings, like the families of lines we talked about before.
Exactly. And the cool thing is that the recovered variety for this curve contains a line that's not part of the original curve.
What? So the recovered variety is bigger than the original?
In a way, yes. It contains this extra line that wasn't there before.
That's really interesting. It's like the recovered variety is revealing something hidden, something that wasn't explicitly part of the original curve.
It is. It shows how the recovered variety can be richer than the original, containing additional components.
Okay, this is all really fascinating. But it's getting late, and I think we should probably take a break here.
Sounds good.
We've covered a lot of ground, but I feel like we're just scratching the surface of this topic.
There's definitely a lot more to explore.
Exactly. So we'll pick up where we left off in the next part of our deep dive.
Looking forward to it.
Me too. Until then, keep those mathematical gears turning.
Absolutely. Welcome back. It's great to continue our exploration of Chow Lam Recovery.
Yeah, I'm really enjoying this deep dive. Before the break, we were talking about how the recovered variety can sometimes be even richer than the original, containing extra components and revealing hidden structures.
It's like the recovered variety is holding on to secrets waiting to be discovered.
Exactly. But, before we get too carried away with these geometric mysteries, I wanted to circle back to something you mentioned earlier, the computational aspects of Chow Lam forms.
Yeah.
We've talked about Plucker coordinates and the general idea of how to calculate the Chow Lam form, but I'm curious about the actual nitty-gritty of it. Like, what are some of the practical challenges that mathematicians face when trying to compute these forms and, actually recover varieties from them?
Yeah, that's a great question. I mean, it's kind of like the difference between having a blueprint for a building and actually constructing it,
Right.
You need both the conceptual framework and the practical know-how to make it happen. And the thing about Chow Lam forms is that they can get computationally very complex, especially when you're dealing with higher dimensional Grassmannians and varieties.
Okay, so it's not just a matter of plugging some numbers into a formula.
No, not at all. A lot of it involves symbolic manipulations, working with variables and equations, trying to find patterns and relationships.
Right, so it's more like solving a really, really complicated algebra problem.
Exactly. And it can get messy really quickly, especially when the number of variables and equations starts to grow. Luckily, mathematicians have developed some powerful tools to help us tackle these computational challenges. One of the key concepts here is something called Grobner bases.
Grobner bases. I think I've heard that term before. Isn't that something to do with computational algebraic geometry?
You're absolutely right. Grubner bases are essential for working with polynomial ideals, which are, fundamental for describing varieties and their Chow Lam forms. Think of a Grobner basis as a special set of generators for a polynomial ideal, a set that has some really nice computational properties.
Okay, so it's like finding a better, more organized way to represent these ideals.
Exactly. And once you have a Grobner basis, you can use algorithms like Bookberger's algorithm to perform eliminations and figure out properties of the Chow Lam locus.
So it's like a powerful tool that allows us to simplify these complex calculations.
Exactly. And there are even software packages like Macaulay 2, Singular, and Coco that are specifically designed to help with these computations.
Wow, so mathematicians are really harnessing the power of computers to tackle these problems.
Absolutely. Computational algebraic geometry is a rapidly growing field, and these software packages are becoming indispensable tools for researchers.
That's really impressive.
Yeah.
But even with these tools, it seems like there's still a lot of room for human ingenuity and insight. We can't just rely on algorithms to do all the thinking for us, right?
No, not at all. Computation is essential, but it's not a replacement for understanding.
Right.
One of the challenges with Chow Lam forms is that they don't always give us the complete picture. The Chow Lam form might not capture all the subtle geometric information about the original variety.
Right, we've seen that in those examples where the recovered variety is different from the original with extra components and all that.
Exactly. And that's where human intuition and geometric reasoning come in.
So it's like we have to be careful, detectives, piecing together the evidence from the Chow Lam form and our understanding of the geometry.
Exactly. We have to be aware of the potential pitfalls and use our knowledge to guide our interpretation.
Speaking of pitfalls, it makes me wonder about the role of representation itself. Like, we've been focusing on the Chow Lam form as a way to represent these varieties, but are there other ways to represent them? And would those different representations give us different perspectives?
That's a really deep question, and it touches on a fundamental aspect of mathematics.
Okay, tell me more.
The way we choose to represent a mathematical object inevitably shapes how we perceive and understand it. Different representations highlight different features and can lead to different insights. So yeah, absolutely, there are other ways to represent varieties, and they can offer different perspectives.
So it's not just about finding the right answer. It's about exploring different ways of seeing and understanding the problem.
Exactly. It's about embracing the richness and complexity of the mathematical world and recognizing that our representations are always partial and evolving.
That's a really beautiful way to think about it. It makes me appreciate the depth and the creativity involved in mathematics.
I agree. And that's what makes this research so exciting. We're constantly pushing the boundaries of what we know, developing new tools, and discovering new connections.
So as we wrap up this part of our deep dive, I'm curious to hear your thoughts on the future of research in Chow Lam recovery. Like, what are some of the big open questions that you think will drive the field forward in the years to come?
Well, one exciting direction is to explore the connections between Chow Lam recovery and other areas of mathematics, like tropical geometry and representation theory.
Oh, those sound interesting.
They are. Tropical geometry offers a more combinatorial perspective on algebraic geometry, while representation theory is all about symmetries. And both of these areas have the potential to shed new light on Chow Lam recovery and its applications.
So it's like we're bringing together different tools and perspectives to gain a deeper understanding of this one concept.
Exactly. And there are some specific open problems and conjectures that are particularly intriguing. Well, for example, conjecture 6.6, which proposes that perfect recovery always holds for generic linear sections of the Grassmannian. That's a big one. Proving or disproving that conjecture would have major implications for our understanding of linear sections and their Chow Lam representations. And another important direction is to develop more efficient algorithms for computing Chow Lam forms and recovering varieties. As we discussed, the computational complexity can be a real bottleneck, so any advances in that area would be huge.
It sounds like there's a lot of exciting work to be done. What advice would you give to young mathematicians who are interested in exploring this area?
That's a good question. I'd say embrace the beauty and the challenge of Chow Lam recovery. It's a field that requires a unique blend of geometric intuition, algebraic skill, and computational thinking. Don't be afraid to ask questions, explore different approaches, and develop new tools. The rewards are immense, both intellectually and in terms of the potential impact on other areas of math and physics.
That's inspiring. It's been an amazing conversation so far. We've really delved into the intricacies of Chow Lam recovery, from the basic definitions and challenges to the computational aspects and potential applications. And, throughout our discussion, we've highlighted the importance of representation, perspective, and the ever-evolving nature of mathematical understanding.
It's been my pleasure. I hope our deep dive has sparked a curiosity in our listeners to learn more about this fascinating area of research.
Absolutely. I know I've learned a lot. And with that, I think we've reached a good stopping point for this part of our deep dive. We'll pick up again next time with a closer look at some specific examples and applications of Chow Lam recovery.
Sounds good. Looking forward to it.
Me too. Until then, keep those mathematical gears turning. Wow. We've really journeyed deep into the world of Chow Lam recovery, haven't we?
We have. It's been quite the exploration of, all these abstract concepts, from Grassmannians to projections to duality.
Definitely. But before we wrap up, I wanted to touch on something we haven't really talked about much yet.
And what's that?
Applications. We've mentioned connections to physics, but I'm curious to hear more about how this whole idea of Chow Lam recovery might actually be used in other fields. Like, what are the practical implications of all this abstract math?
That's a great question. And, it's one of the amazing things about math, how even the most abstract ideas can often find surprising applications in seemingly unrelated areas.
I agree.
And while the field of Chow Lam recovery is still relatively young, there are already some tantalizing hints of its potential impact.
Oh, really? Like what? Can you give us some specific examples?
Absolutely. So one area where Chow Lam recovery could play a role is in computer vision and image processing. Imagine you're trying to reconstruct a 3D scene from a bunch of 2D images.
Oh, yeah, that's a classic problem.
Right. And it turns out that this problem has a lot of similarities to recovering a variety from its projections.
Interesting. So instead of thinking about varieties and Grassmannians, we're thinking about real-world objects and their images.
Exactly. The underlying mathematical principles are quite similar, and the techniques we've developed for Chow Lam recovery could potentially lead to new algorithms and insights for solving these kinds of problems in computer vision.
That's really cool. I never would have guessed that connection.
It's pretty amazing how these abstract ideas can find such practical uses. And, another potential application is in the field of robotics and motion planning.
Robotics. Okay, tell me more about that.
Sure. So imagine you have a robot that's trying to navigate through a complex environment. The robot needs to plan a path that avoids obstacles and reaches its destination efficiently, right?
Makes sense.
Well, this path planning problem can be formulated in terms of finding a curve in what we call a configuration space. It's a space that represents all the possible positions and orientations of the robot.
Okay, I see. So we're like representing the robot's movements as a curve in this special space.
Exactly. And the cool thing is that we can potentially use Chow Lam recovery techniques to reconstruct the robot's trajectory from partial observations, or even to design optimal paths that satisfy certain constraints.
Wow. So we're basically using algebraic geometry to help robots move around in the real world.
You got it. It's still early days for this kind of application, but the possibilities are very exciting. And, there's another area where Chow Lam recovery could make a big impact.
Oh, yeah. What's that?
Data analysis and machine learning. Think about it. You have a massive data set represented by points in a high-dimensional space.
Okay, yeah, that's pretty common these days with all the data we're collecting.
Right, and often these data points might actually lie on or near a lower dimensional variety.
I see. So there's some underlying structure to the data.
Exactly. And Chow Lam recovery techniques could help us identify this underlying structure. This could lead to more efficient algorithms for data compression, dimensionality reduction, and pattern recognition.
Wow, that's amazing. So we're using the geometry of varieties to understand patterns in data.
Precisely. And as we continue to develop our understanding of Chow Lam recovery, I think we'll see even more applications emerge in unexpected places.
I'm sure you're right. It's clear that this is a really vibrant and promising area of research.
It is. And, it's really inspiring to see how these seemingly abstract mathematical ideas can have such a profound impact on the world around us.
I agree. It's been an incredible journey exploring this world of Chow Lam recovery with you. We started by defining the Chow Lam form and exploring the challenges of recovering a variety from its projections. We saw how different families of varieties, from ruled quadric surfaces to Schubert varieties to positroid varieties, each have their own unique recovery properties.
And we also delved into the computational aspects, the challenges of interpretation, and even touched on some of the potential applications in other fields.
Yeah, we've covered a lot of ground. And throughout our discussion, I think one of the key takeaways has been this idea of representation and perspective. How the way we choose to represent a mathematical object can shape our understanding of it, and how seeking multiple perspectives can lead to new insights and discoveries.
Absolutely. And it's that spirit of exploration and curiosity that will continue to drive progress in this field and in mathematics as a whole.
Well said. I want to thank you again for sharing your expertise and insights with us. It's been a true pleasure.
The pleasure was all mine.
And to our listeners, thank you for joining us on this mathematical adventure. We hope you've enjoyed the journey as much as we have. Keep exploring, keep questioning, and keep pushing the boundaries of knowledge. Until next time. Welcome to another deep dive. Today we're going to be tackling Chow Lam forms and using them to recover subvarieties of Grassmannians from their projections. We've got this paper here, and it looks like it's going to be a fun one.
Yeah, it looks like it goes into some pretty interesting stuff. And it poses a very particular problem. You see, unlike projective varieties, which can always be recovered from their Chow forms, the same isn't true for varieties in Grassmannians.
So we're talking about, we know the shadow of something, but we can't recreate the object perfectly just from the shadow. Okay.
Exactly. And the Chow Lam form, which, generalizes the classical Chow form to Grassmannians, it doesn't always let us fully get back to the original variety.
Okay, before we get too deep into this, I think we need to, remind ourselves what exactly we're dealing with here. We're talking about Grassmannians and projections and these Chow Lam forms. Maybe we can start with a super quick recap for anyone who needs it.
Absolutely. So let's begin with Grassmannians. A Grassmannian denoted Gr, K-A-A-N, is a space that parameterizes all the k-dimensional linear subspaces of an n-dimensional vector space.
Okay, so all the possible k-dimensional subspaces within a given n-dimensional space.
Exactly. So you can think of it like GR1 represents the set of all lines in an n-dimensional projective space.
Okay, got it. And then what about projections? How do those fit into this whole picture?
So imagine you have a higher dimensional space and you're trying to map points from that space onto a lower dimensional one. That's kind of like a projection, right? And in this context, we're specifically dealing with projections of subspaces from one Grassmannian to another Grassmannian, but of a lower dimension.
Okay, so projecting from a bigger space to a smaller space.
Right. And the paper uses a matrix Z to kind of induce this map between these Grassmannians.
Gotcha. So if you look at equation 1 in the paper, it shows how this Z acts on a subspace represented by a matrix. It basically projects each column of that matrix onto this lower dimensional space.
Exactly. And when you set K equal to 1, it actually generalizes that familiar idea of lineal projections, but between projective spaces.
Okay, so we've got our Grassmannians and we've got our projections. Now, where does this Chow Lam form come into play?
All right. So the Chow Lam form, which is denoted by CL and then subscript V for a subvariety V. This is basically a polynomial that holds information about all the projections of V.
So it's like a blueprint.
In a way, yes. It's kind of like a generalization of the classical Chow form, but for projective varieties. The main idea is that if we have enough information about the projections of V, which this Chow Lam form captures, we might be able to rebuild V itself.
Okay, so the paper's exploring when this is possible and when it's not.
Exactly.
Yeah.
The recovery problem that's at the heart of this whole thing, it asks, given a subvariety V in a Grassmannian, can we figure out what V is just from knowing its projections?
So its projections are like Z of V for various matrices. Z. Got it.
Yeah.
And is it always possible?
Well, that's the thing. Turns out it's not always possible. Equation 2 in the paper actually shows that while V is always contained within the intersection of all the preimages of its projections, sometimes this intersection can actually be larger than V.
Oh, so there might be other subvarieties that have the same projections as V.
Exactly. So we wouldn't be able to tell them apart just from their Chow Lam forms.
So the shadow isn't unique to that one object. That's kind of wild. Now, the paper mentions this connection to particle physics, specifically scattering amplitudes in N4 supersymmetric Yang-Mills theory. I know this might seem like a bit of a jump, but can you give us a little insight into how these things are connected?
Yeah, it does seem like a bit of a leap, right? But it shows how these seemingly different areas of math and physics can be connected in really cool ways. So the projections we've been talking about actually play a role in the amplituhedron, which is this geometric object that's used to compute scattering amplitudes in certain quantum field theories.
Okay, hold on. So we're going from like abstract algebraic geometry to like the world of subatomic particles.
It's wild, right? And this amplituhedron thing, it actually lives in what's called the positive Grassmannian.
Okay, and what is the positive Grassmannian?
So it's basically a subset of the Grassmannian where all the Plucker coordinates are non-negative.
Oh, Plucker coordinates. I
Yeah.
remember those. Just a quick refresher. What are those again?
You got it. So Plucker coordinates are essentially a way to give coordinates to subspaces within a Grassmannian. They're like determinants of certain submatrices of a matrix representing that subspace.
Okay, so in the positive Grassmannian, all those determinants have to be positive or zero.
Exactly.
Okay.
And the amplituhedron is built from projections of this positive Grassmannian, but using matrices that have positive maximal Mainers.
Okay, that's super interesting. Now, I also remember reading about these things called positroid varieties. Can you remind us what those are and how they fit into all of this?
Yeah, for sure. Positroid varieties are kind of special. They form the boundaries of this positive Grassmannian.
Oh, so they're like the edges or faces of this positive Grassmannian shape.
Yeah, you could think of it that way. And they have a really neat connection to these things called matroids, which are actually from combinatorics.
So we're connecting to other parts of math, too.
Always. And I think it's worth noting that Thomas Lem's work on positroid varieties and their projections was actually one of the inspirations for developing this whole Chow Lam form idea.
Oh, wow. So it all comes full circle. Okay, so we've got our Grassmannians, our projections, our Chow Lam form, and these positroid varieties. Let's talk about the Chow Lam locus itself. What is it and how is it defined?
Right. So imagine you have a subvariety V in a Grassmannian or AN. The Chow Lam locus, which is denoted CL with a subscript V, is the set of all NR plus K1 dimensional subspaces that contain at least one K-dimensional subspace from V.
Hold on. NR plus K1 dimensional subspaces.
Yeah, where R the dimension of the space where we're projecting onto.
Okay, so it's like we're expanding outwards from V and looking at all the larger subspaces that kind of enclose some part of V.
Precisely. And if this Chow Lam locus happens to be a hypersurface, meaning it has codimension 1, then it can be defined by a single polynomial equation. And that equation is what we call the Chow Lam form, denoted CLV. And example 1.1 in the paper gives us a nice visual for this. It considers a curve V in GR24, and it shows that its Chow Lam locus is actually the dual surface of the surface that's swept out by all the lines represented by V.
So it's like we're thinking of the lines that are parameterized by V as sweeping out this surface, and then the Chow Lam locus is like a mirror image of that surface, but in this dual projective space.
Exactly. And it's worth noting that when A is equal to 1, the Chow Lam form actually reduces to the classical Chow form for projective varieties.
Oh, so it really is a generalization of the classical case. Now, Lemma 1.2 gets into the nitty-gritty of the geometry of these projections, and it gives us a pretty neat interpretation of the fibers of the projection map Z. It uses this concept of joins, which might sound a bit intimidating, but it's a pretty intuitive idea. Can you break it down for us?
Sure. So a join of two subspaces, say P and Q, is basically the smallest subspace that contains both of them. Lemma 1.2 says that a subspace P is in the pre-image of ZV if and only if the join of P with KZ, which is the kernel of the matrix Z transpose, contains a point from the original variety V.
So we're taking P and we're kind of connecting it to this special subspace KZ, and we're seeing if that connection actually intersects with V. If it does, then P is part of the pre-image of ZV.
Exactly. It's a nice way to visualize what's going on with these projections. Now, with this in mind, the paper introduces the concept of the recovered variety, which is denoted WV.
Okay, and this is where things start to get interesting.
Right.
So this recovered variety WV is basically all the subspaces P that have this property. Any larger subspace containing P also contains a point from V. So it's like we're trying to rebuild V by looking at all these subspaces P that are kind of close to V in this way.
Exactly. And the crucial point here is that WV always contains V, but it could be bigger. And this brings us back to that question of recovery. Can we always get back to V just from WV?
Right, because if WV is bigger than V, then there's extra stuff in there that wasn't part of our original variety.
Yeah.
We know that with the classical Chow form, recovery is always possible. But what about with the Chow Lam form? Can we always uniquely get back to the original variety?
Well, unfortunately, no. Example 1.4 actually gives us a counterexample using a ruled quadric surface, which is a surface that can be swept out by a family of lines.
Oh, so similar to that surface we were visualizing earlier with the curve in GR24.
Exactly. And what's interesting here is that on this ruled quadric surface, you can actually find two different curves that have the same Chow Lam locus.
So if we only knew the Chow Lam form, we wouldn't be able to tell which of those curves was the original one. So it's not unique.
Right.
Okay, that's pretty wild.
Yeah.
It means that the Chow Lam form doesn't always give us enough information to uniquely identify the variety. So the recovery problem with this Chow Lam form, it's way more subtle than the classical Chow form case.
It really is. And understanding when this recovery is possible and when it's not is one of the main goals of this paper.
Okay, so we've established that recovery is not always a sure thing. Let's switch gears a bit and talk about how to actually compute these Chow Lam forms in this recovered variety. The paper mentions primal and dual Plucker coordinates, which I think are key to understanding the computational side of this. Can you break those down for us?
Of course. So as we talked about before, Plucker coordinates give us a way to represent subspaces in a Grassmannian, but using numerical coordinates. And they're basically determinants of certain submatrices of a matrix representing that subspace. Now we've got two types, primal and dual.
Okay, so given a k-dimensional subspace in an n-dimensional vector space, which is represented by a k by n matrix, the primal Plucker coordinates are all the k by k minors of that matrix.
Exactly. And the dual Plucker coordinates are defined in a similar way, but we use a different matrix that represents the same subspace, but viewed as like the projectivization of the kernel of a linear map.
Okay, so both types are based on determinants, but they're calculated using slightly different representations of that same subspace.
You got it. And you can see a concrete example of this in equation 4 in the paper.
Oh yeah, it shows all the primal and dual Plucker coordinates for GR35. Okay, so to compute the Chow Lam form, the paper outlines a procedure that involves building something called the incidence variety. What is that, and how does it help us with this computation?
So the incidence variety is denoted by the Greek letter grade, and it's a way to describe the relationship between a subspace and a larger subspace that contains it. It's basically the set of all pairs, PQ, where P is a k-dimensional subspace, and it's contained in a larger NR plus K one-dimensional subspace Q.
Okay, so it's like we're creating a new space that keeps track of all the ways to fit a k-dimensional subspace inside a larger subspace.
Exactly. And the way this helps us with the Chow Lam form is that we combine the equations that define V with the equations that define this incidence variety, and then we eliminate certain variables to get the Chow Lam form.
So we're solving a system of equations where the unknowns are the Plucker coordinates.
Precisely. And by carefully choosing which variables to eliminate, we can isolate the equation that defines the Chow Lam form.
Got it.
And example 2.1 illustrates this beautifully for the case K2N4 and R3.
So we're looking at lines and planes in a three-dimensional projective space, and the equations make sure that a line lies within a plane.
Exactly. And we use the Plucker coordinates of the lines and the planes to express those conditions, but algebraically.
Okay, so once we have those equations, we combine them with the equations that define our original variety V, and then eliminate variables until we get our Chow Lam form.
Exactly. It's a step-by-step process that can be computationally intense, but it's a systematic way to get the Chow Lam form for a given variety.
Okay, so now that we have the Chow Lam form, we can work backwards and find the recovered variety WV. How do we do that?
So WV can be computed from the Chow Lam form by expanding the dual Plucker coordinates of a join of two subspaces, and then we collect the coefficients as polynomials in the Plucker coordinates of one of the subspaces. And these coefficients will give us the defining equations for WV.
So we're basically decoding the information that's in the Chow Lam form to rebuild this recovered variety. But like we said before, there's a catch, right? This recovered variety, it might have points that weren't in the original V, and it might even have a higher dimension.
That's right. It's like the recovery process is adding extra stuff. And example 2.2 shows this with a singular quintic curve in projective space. It shows that the recovered scheme, while algebraically equivalent to V, is scheme theoretically different.
Okay, wait, what does that mean? Scheme theoretically different.
So it means that the recovered scheme has an embedded component, but at the singular point, which is indicating some extra structure there beyond just a set of points.
Okay, so even though the underlying point sets are the same, there's this extra multiplicity or thickness at the singular point in the recovered scheme.
Exactly. And this difference is reflected in the defining equations of that recovered scheme.
Got it. And then example 2.3 kind of takes this a step further and looks at what happens when we have a curve in GR24 that's defined by tangent lines to that singular quintic curve from the previous example.
Right. And in this case, the recovered scheme has three primary components. One represents the original curve, and the other two represent the two singular points.
It's like the singularities are leaving their mark on the recovered scheme,
Yeah.
giving rise to these extra components.
Exactly. And then example 2.4 really shows us how much bigger WV can be than V. It uses a Schubert variety W and a generic subvariety V inside of that.
Schubert varieties, just a super quick reminder what those are.
So they're special subvarieties in the Grassmannian defined by conditions on how the subspaces intersect with a fixed flag. They have a really nice geometric structure, and they're fundamental to the study of Grassmannians.
Okay, so there are these important subvarieties with these special properties, and in this example we have a Schubert variety W and a smaller variety V that's contained within W.
Right, and what happens is that for certain projections, W and V actually have the same image, so W becomes part of WV.
Hold on, so even though V is much smaller than W, the recovered variety contains all of W.
Yep. And they even compare their dimensions. W has codimension n minus k and dimension k minus 1 times n minus k, while V has dimension k plus 1. As k gets bigger, that difference in dimensions becomes really drastic.
Wow. So the recovered variety can be a lot bigger and more complex than the original variety. It's almost like the recovery process is trying to fill in gaps or smooth out the original variety, and that's what introduces these extra components.
That's a great way to think about it, yeah. The Chow Lam form, it captures information about the projections, but that might not be enough to fully determine the variety itself. And when that happens, the recovered variety will be larger, and that reflects that ambiguity in the projection data.
Okay, that makes a lot of sense. So we've seen some specific examples of how the recovered variety can be different from the original one. Now, the paper goes on to develop a general criterion for whether a point is in this recovered variety. And this is where things get a bit more technical, but I think it's worth getting into the details.
Definitely. So this criterion, it's based on the dimensions of certain subvarieties that are associated with a given point.
Okay, so the paper introduces this stratification of V based on the dimension of its intersection with a fixed subspace P of dimension k minus 1.
Right.
And this leads to the definition of these subvarieties VPI, which are the subsets of V where the intersection with P has dimension I.
Exactly. And then Lemma 3.1 gives us a formula for calculating the dimension of the Schubert variety of subspaces that contain a fixed subspace Q. And this sets us up for the main recovery criterion, which is theorem 3.2.
And this theorem is really the heart of this section. It gives us a necessary condition for a point P to be in WV.
Yeah.
It says there must exist an I such that the dimension of VPI is at least k minus I minus 1 times R minus k.
Exactly. So it's a dimension argument. If P is in the recovered variety, then certain subvarieties have to have at least a certain dimension.
Okay, and the proof of the theorem relies on the surjectivity of the projection map from the incidence variety. It's basically saying that if the projection map is surjective, then the dimensions of these subvarieties have to satisfy this inequality.
Precisely. And then they illustrate this with a surface in GR3N, walking through the conditions of the theorem and showing how P must either meet every point of V or meet a one-dimensional family in a line or be a point in V itself.
Right, so it's a really concrete example of how to apply the theorem. But they also caution that while the theorem gives a necessary condition, it's not sufficient. So even if VPI has a large dimension, the projection map could still have high-dimensional fibers, which would prevent surjectivity.
Exactly. There might be other reasons why a point isn't in the recovered variety, even if it satisfies the dimension condition.
Got it. And example 3.3 actually gives us a counterexample to the converse of theorem 3.2.
Right. It uses a four-dimensional subvariety V1 in GR4N and a larger seven-dimensional variety V that contains it.
Okay.
And they show that even though the dimension condition of theorem 3.2 is met for a point P, there is a subspace containing P that doesn't contain any point from V.
So P is not in the recovered variety, even though it satisfies the dimension criterion.
Exactly. And it shows how important it is to really analyze the geometry of what's going on and not just rely on these dimension checks.
Absolutely. Okay, so we've delved into the general criterion for
Yeah.
a point to be in the recovered variety, and we've seen how it works and how it can sometimes fail. Now, the paper moves on to explore this connection between the Chow Lam locus and the idea of dual varieties.
This is where things get really interesting, I think. because it reveals this deeper geometric structure that underlies the Chow Lam form.
Okay, I'm intrigued. So they introduce this XV, which is the union of all K1 dimensional subspaces that are contained in a subvariety V of Gr. So basically, we're taking all the K1 dimensional slices of V and putting them together.
Precisely. And to understand the connection to dual varieties, we should quickly remind ourselves what a dual variety is.
Right. So a dual variety is like a mirror image of the original variety, but in this dual projective space. And the points of the dual variety correspond to hyperplanes that are tangent to the original variety. So it's like we're looking at the original variety, but through the lens of its tangent hyperplanes.
Exactly. And proposition 4.1 links the dual variety of XV and the Chow Lam locus.
Okay, so it says that for subvarieties of dimension K1, the dual of XV is always contained in the Chow Lam locus.
Yes, and they are equal when they have the same dimension.
So there's this tight connection between the dual of this union of slices variety and the Chow Lam locus.
Exactly. And it goes on to say that a K1 dimensional subspace P is in the recovered variety WV if and only if its dual space is contained in the dual of XV.
So there's like this duality at play. If a point is in the recovered variety, then its dual is in the dual of XV. And this leads to some interesting consequences when we're thinking about curves in Gr.
Right. So for curves in Gr and Un that have a Chow Lam form, we either have the classical Chow form scenario where K is 1, or we have the case where K is 2 and R is 3.
And in that second case, proposition 4.1 directly applies, meaning that the Chow Lam form defines the dual variety to XV whenever this dual is non-degenerate.
Precisely. So for curves in GR2N, the Chow Lam form essentially gives us a way to describe the dual variety of XV.
Okay, so this observation can be extended to prime dimensional subvarieties too, right?
Right. Corollary 4.2 talks about this. It states that for a P1 dimensional subvariety V in Gr-M, clam K, A-N, with P being a prime number, a Chow Lam form exists only if K is equal to P and the Chow Lam locus is in the dual projective space.
So the fact that P is a prime number is important here.
Yes, it dictates that K has to be prime too, and the Chow Lam locus has to live in the dual projective space.
Okay, and then for the specific case of curves where P is 2, we have an even stronger statement in Corollary 4.3.
Right, it says that for a curve V in GR2N where XV is not a cone, a line L is in the recovered variety WV if and only if it's completely contained within XV.
So if this union of slices variety XV is not a cone, then the recovered variety is just the lines that are fully inside of XV.
Precisely. And the reason for this is pretty elegant. If XV is not a cone, then its dual is a hypersurface, and it coincides with the Chow Lam locus. And a line that's not fully contained in XV can't be in the recovered variety because its dual point won't be in the dual of XV.
Okay, that makes sense. So let's see how this works in some concrete examples. Example 4.4 introduces a Hertzsprung surface.
Right, which we can think of as a ruled surface.
Ruled surface meaning?
It's a surface that can be swept out by a family of lines, and they show how embedding a Hertzsprung surface gives us a curve in GR2N.
Okay, and in this case, the recovered variety contains a line that's not part of the original curve.
Exactly. So again, we're seeing the recovered variety contain extra stuff that wasn't there originally.
And to make things even more concrete, they look at the case where A is 1, and they give explicit parametric equations for the surface and the lines and the ruling.
Yeah, it really shows how the curve V is constructed. And it turns out the Chow Lam form can be computed parametrically.
And what happens?
Well, if recovered scheme, it contains this extra fat point, which represents a line that's obtained by letting one of the parameters go to infinity.
So we're adding an extra point at infinity that corresponds to a special line in the ruling.
Exactly. It's another example of how these additional components can show up in the recovered scheme.
Okay, now the paper also mentions what happens if you have multiple lines in the surface scroll XV that aren't rulings. They say that in this case, the scroll must lie within a three-dimensional projective space, and this leads to a surface with specific multiplicities along these non-ruling lines.
Right, and calculating these multiplicities involves looking at the surface as like a birational image of a projective bundle over V, and understanding how the degrees of the maps relate to those multiplicities.
So it's a more technical argument involving projective bundles. Okay, got it. Then example 4.5 shows how a curve that maps to both a line and another curve gives us a scroll surface where the line is in the recovered variety, but not in the original curve.
Right, and this illustrates how the geometry of the original variety and its mappings can influence the structure of the recovered variety.
And example 4.6 generalizes this to surfaces. using a surface with multiple linear systems to construct a four-dimensional scroll in a higher dimensional projective space.
Yeah, and this leads to a surface in the Grassmannian where the recovered variety contains a plane that isn't part of the original surface.
Okay, so we've seen tons of examples of how the recovered variety can be larger than the original variety. Now, in Section 5, the paper goes into multi-ruled varieties, which are varieties that can be swept out by multiple families of linear subspaces.
Right, multi-ruled varieties are a natural extension of ruled surfaces,
Mhm.
and they give us a lot of examples to play around with in terms of this Chow Lam recovery.
And Corollary 5.1 uses Proposition 4.1 to give us a condition for when two K1-dimensional subvarieties have the same Chow Lam locus. Basically, if the duals of their union of slices varieties are the same, then their Chow Lam loci will be the same.
Exactly. And the paper gives a bunch of examples of this using different kinds of multi-ruled varieties like Segre varieties and determinantal hypersurfaces.
Okay, so example 5.2 talks about Segre varieties, which are varieties that can be ruled by two families of subspaces. And this results in two different subvarieties in the Grassmannian that have the same Chow Lam locus.
Right. And then example 5.3 generalizes this to Segre varieties with more than two factors, showing that you can have multiple subvarieties with the same Chow Lam locus.
Okay, and then example 5.4 shifts gears to linear determinantal hypersurfaces, which are defined by the vanishing of a determinant. And they connect this back to Segre varieties by looking at a Segre variety as the set of rank 1 matrices.
Exactly. And we see how this leads to a determinantal hypersurface as the Chow Lam locus, and how projections of the Segre variety give us more examples of multiple subvarieties with the same Chow Lam form.
And finally, example 5.5 delves deeper into a specific case of example 5.4 where K is 3.
Yeah, and we get this cubic surface, and we see how the degeneracy locus of a matrix that's constructed from the defining equation of the surface tells us the degree of the Chow Lam form. And we even see this cool thing called a double six on the cubic surface.
So multi-ruled varieties give us all these interesting examples of how Chow Lam recovery can be tricky and how the recovered variety could be bigger than the original variety.
Absolutely. And they highlight the complex relationship between the geometry of the variety and the algebraic properties of the Chow Lam form.
Okay, so we're ready to move on to the last section of the paper, which focuses on Schubert arrangements.
Sounds good.
All right, so Schubert arrangements. To refresh everyone, Schubert varieties are those special subvarieties in a Grassmannian that are defined by conditions on how subspaces intersect with a fixed flag. They use partitions to denote them, which are basically sequences of integers that encode those intersection conditions.
Right. Schubert varieties are fundamental to the geometry of Grassmannians. They have a rich combinatorial structure, and they pop up in lots of different areas of math. And in this section, the paper looks at what happens when we use this Chow Lam recovery on intersections of Schubert varieties, which are called Schubert arrangements.
So we're looking at linear sections of the Grassmannian defined by Schubert divisors. And they use this notation, a Schubert, and then a superscript J and a subscript 1, which represents the intersection of J Schubert hyperplane sections.
Exactly. So A with a 3 superscript and a 1 subscript would represent the intersection of 3 Schubert hyperplanes.
Okay, got it. And the question is, what happens when we try to recover these Schubert arrangements using the Chow Lam form? Do we get back the original intersection, or do we end up with something bigger like we saw in some of the earlier examples?
That's the question, and the answer, as you might expect, is that it can be complicated. They give some examples to show all the different things that can happen.
So let's start with example 6.1, which looks at a threefold in GR255 that's defined by the intersection of 3 Schubert divisors. So we're looking at A with a 3 superscript and a 1 subscript in GR25. And they find that the recovered variety for this threefold actually has extra Schubert components.
Yeah, so even though we start with a very specific intersection of Schubert varieties, the recovery process adds in extra components that are themselves Schubert varieties.
So the recovery is pulling in extra Schubert varieties that weren't part of the original intersection.
Right.
And then example 6.2 goes a step further and looks at a codimension 7 variety in GR2 NOD, defined as A with a superscript N2 and subscript 1.
Exactly. And again, we see these extra components appear, and whether or not they exist depends on the value of N, which is the dimension of the ambient vector space.
And the paper explains why these recovered components show up. And it's some really clever geometry. Essentially, they show that if you have a generic subspace in the Chow Lam locus, you can pick a specific subspace that leads to the existence of a common transversal to several planes. And this means that there are these additional Schubert components in the recovered variety.
It's a really nice interplay between the geometry of the Schubert varieties and the algebra of that Chow Lam form.
Yeah, definitely. And these examples show a pattern which the paper summarizes in Theorem 6.3. This theorem lists out these recovered components for ILA, with a superscript key plus 1 and a subscript 1, assuming the n is large enough.
Right, so we can predict what these extra components are in certain cases.
But they also point out that this theorem doesn't include all possible recovered components, especially when Rni, which is the dimension of the intersection of a subspace with the Schubert variety, is small.
Exactly. There are cases where you get additional components that aren't predicted by the theorem, like the Schubert variety A sub 2000, A sub 3 sub, and G 2 to 7. This one appears in the recovered locus, but it's not covered by Theorem 6.3.
So there are subtleties and special cases we need to be aware of. And based on these observations, they propose conjecture 6.4, which says that if I is greater than or equal to A, then all the recovered components will have that form described in Theorem 6.3.
It's an interesting conjecture, and if it's true, it would make our understanding of these recovered components much simpler.
Okay, so we've gone over specific examples and a general theorem for recovering these Schubert arrangements. Now let's zoom out and ask a broader question. Do generic linear sections of the Grassmannian even have these recovered components?
That's a really hard question to answer generally. We're asking if those extra components are common or specific to certain cases.
Right. And to get some insight, they look at the case of curves and find that a generic curve in GR2n only has recovered components when n is 4 and the curve is a conic.
Right, so in that specific case, things are pretty well behaved. But for generic curves in GR2n, when n is bigger than 4, we don't get those extra components in the recovered variety.
Okay, but what about higher dimensions? Does that pattern hold up?
Proposition 6.5 looks at a threefold example, and they prove that this one doesn't have recovered components.
And this leads to conjecture 6.6, which says that generic linear sections of GDEN that have dimension k times n minus r plus 1 shouldn't have any recovered components.
It's a really interesting conjecture. It's suggesting that for generic linear sections of a certain dimension, we might not expect to see those extra components in the recovered variety.
Okay, so there's some evidence that those extra components might be less common for generic linear sections, at least in certain dimensions. Now back to those positoid varieties we discussed earlier. The paper reminds us that those are boundary components of the positive Grassmannian.
Exactly, and they're a special class of Schubert varieties that have a very nice combinatorial structure. They're defined by positivity conditions on their Plicker coordinates, and they relate to objects called matroids from combinatorics.
And the cool thing is that the class of examples from Theorem 6.3 includes certain positoid varieties, specifically the ones that can be cut out by generic Schubert divisors. So there's a connection between those general results about Schubert arrangements and this specific family of positoid varieties.
Exactly. It suggests that the recovery process for positoid varieties might behave similarly to what we've seen for more general Schubert arrangements.
And to illustrate this corollary, 6.7 shows that a specific family of positoid varieties in GRUR2n actually has recovered components.
Right. This is a concrete example where the recovered variety for a positoid variety is larger than the original one.
So we're seeing all these connections between the geometry of Schubert varieties, the algebra of the Chow Lam form, and the combinatorics of positoid varieties.
Absolutely. And the paper ends this section by suggesting that looking at WV for positoid varieties in a more systematic way would be a good area for future research. It's like a call to action for mathematicians to dig deeper into the Chow Lam recovery in this specific setting.
So there are lots of open questions and avenues to explore. We've seen how the Chow Lam form can be a powerful tool for studying these subvarieties of Grassmannians, but it doesn't always allow us to easily recover the original variety. The recovered variety can be bigger and have extra components, and understanding when this happens and what those components are is a really challenging problem.
Definitely. And this paper gives us some criteria and specific examples to help us understand it better. But there's still a lot to figure out, especially when it comes to those special classes of varieties like Schubert arrangements and positoid varieties.
Okay, so we've made it to the end of this paper. It's dense, but it's super insightful. It's clear that the Chow Lam recovery problem is really complex and connects to so many different parts of math and physics.
Totally. It really shows how interconnected math is and how algebraic geometry can help us understand things that seem totally separate.
Now, before we finish this deep dive, I want to go back to that connection to particle physics and the amplituhedron. The paper mentions that these projections and Chow Lam forms have implications for understanding scattering amplitudes in certain quantum field theories. Can you explain that connection a bit more?
Sure. So the amplituhedron, as we mentioned earlier, is this geometric object that describes scattering amplitudes of certain particle interactions. And it lives in the positive Grassmannian, which is a subset of the Grassmannian, where the Plucker coordinates are all non-negative.
Okay, so it's like we're focusing on a special part of the Grassmannian where everything is positive.
Exactly. And the amazing thing is that the amplituhedron is built from projections of this positive Grassmannian, but using special matrices that have positive maximal minors. So those same projections we've been talking about in the paper, the maps between Grassmannians that are created by matrices, they actually help build this object that tells us about particle interactions.
It's like these abstract algebraic ideas like Grassmannians and projections are describing something deep about the physical world.
It really is, and the connection goes even deeper. The boundaries of the amplituhedron are closely related to positroid varieties. And those, as we've seen, are these special subvarieties of the Grassmannian with a cool combinatorial structure. So the combinatorics of positroid varieties is connected to the physics of particle interactions.
Wow, that's a mind-blowing connection. So if we can understand the Chow Lam recovery problem for positroid varieties better, which is one of the open questions the paper brings up, it could help us understand scattering amplitudes and the amplituhedron.
Absolutely. If we can figure out how to recover positroid varieties from their projections, it could give us new ways to understand the structure of the amplituhedron and how it describes scattering amplitudes.
That's really exciting. It shows how connected math and physics are and suggests that more research in this area could lead to some huge discoveries.
I totally agree. It's a great example of how math can help us understand the world around us.
Okay, so to wrap up our deep dive, we've learned that recovering a subvariety from its Chow Lam form isn't always possible, unlike the case with projective varieties and the classical Chow form.
Right. The Chow Lam form generalizes the classical Chow form, but it doesn't always give us enough information to know for sure what the original variety was. That's because projections from Grassmannians can lose information. So we can't always perfectly rebuild the original variety from just its projections.
And we saw some specific examples of this, like that ruled quadric surface, where two different curves had the same Chow Lam locus. That really showed us that recovering varieties using the Chow Lam form is a lot trickier than using the classical Chow form.
Yeah, and those examples highlighted how important it is to understand when we can recover the original variety and when we can't. The paper gave us some criteria based on things like the dimensions of certain subvarieties that can help us figure out if recovery is possible.
Right, and even when we can recover the variety, things can still get pretty complicated. We saw how even simple linear sections of the Grassmannian can end up with these extra components in the recovered variety. It's like the recovery process is adding in extra pieces that weren't there originally.
It is surprising, and it tells us that the Chow Lam form can sometimes give us results that are way more complex than we might expect. And it shows how important it is to carefully think about the geometry to fully understand the recovered variety.
And then there's the connection to Schubert varieties and positroid varieties. We learned that certain combinations of Schubert varieties, called Schubert arrangements, can also have these recovered components. And this is super interesting because positroid varieties, which are a special type of Schubert variety, are connected to particle physics through the amplituhedron.
Exactly. Positroid varieties have this special structure that encodes information about how particles scatter. So figuring out how to recover positroid varieties from their projections could help us understand the amplituhedron and how it connects to the physical world.
That's a super exciting possibility. It suggests that research in this area could lead to new discoveries in both math and physics.
Totally agree. This paper has shown us a really interesting area of math, and there's still a lot to discover.
So what are some of the big open questions and areas for future research that you think are worth exploring?
One of the most exciting questions is whether we can understand the recovered variety for positroid varieties in more detail. Can we predict exactly what those extra components will look like and how they relate to the structure of the positroid variety?
It would be awesome to have a kind of dictionary that connects the properties of a positroid variety to the specific recovered components. That would be a huge step forward.
Definitely. And that kind of dictionary could help us understand the amplituhedron and scattering amplitudes better. It could show us how these abstract math ideas connect to the physical world.
Another cool direction would be to look at the recovery problem for other types of varieties. We've mainly focused on Schubert varieties and positroid varieties, but there are tons of other varieties in Grassmannians that might behave in interesting ways under Chow Lam recovery.
That's a great point. We could look at varieties defined by determinants or varieties related to representations of Lie groups. It could lead to new geometric discoveries and connections to other areas of math and physics.
And we can't forget about the challenge of finding better algorithms for computing Chow Lam forms and recovered varieties. The methods in this paper are a good starting point, but as the varieties get more complex, the calculations get really hard.
Absolutely. Better computational tools would help us do more research and could also be useful in fields like computer vision and robotics, where Grassmannians are used to represent and analyze data.
So there are a ton of possibilities for future research. This paper has given us a glimpse into this really cool area of math, and it's clear that there are many more discoveries to be made.
I completely agree. This journey through Chow Lam forms and Grassmannian projections has been amazing, and I can't wait to see what we find next.
Well, that's a wrap for our deep dive into Chow Lam recovery. Thanks for joining us, and we hope you learned something new and exciting.
If you have any thoughts or make any discoveries of your own, we'd love to hear about them. Keep exploring.
Wow, that was a lot to take in. From Grassmannians and projections to Chow Lam forms and positroid varieties, my brain is definitely full.
It was a lot. But it was so cool, right? We went deep into the geometry of Grassmannians and saw how hard it can be to get back to the original variety just from its projections.
Totally. And what's crazy is that this isn't just theoretical. It connects to physics, too, with that whole amplituhedron thing and calculating scattering amplitudes.
Yeah, it's mind-blowing that those abstract algebraic objects, those Grassmannians and projections, are somehow describing how particles interact.
Okay, so big picture, what are the main takeaways from all this?
So first we learned that unlike projective varieties, which can always be recovered from their Chow forms, varieties and Grassmannians can't always be recovered from their Chow Lam forms.
Right, so the Chow Lam form is like a generalization of the classical Chow form, but it doesn't always give us enough information to perfectly recreate the original variety.
Exactly, because when you project from a Grassmannian, you can sometimes lose information, so you can't always rebuild the original thing.
And we saw examples of that, like that ruled quadric surface where two different curves had the same Chow Lam locus.
Yeah, that showed us that recovering varieties using the Chow Lam form is way more complicated than using the classical Chow form.
And even when you can recover the variety, it can get really messy. We saw how simple linear sections of the Grassmannian can have those extra components in the recovered variety. Like the recovery process is throwing in extra pieces that weren't there before.
Yeah, it's one of the most surprising things we saw. It means the Chow Lam form can sometimes give us results that are way more complicated than we'd think. And it shows how important it is to really understand the geometry of what's going on.
And then we have that whole connection to Schubert varieties and positroid varieties.
Right.
We saw that certain combinations of Schubert varieties can also have those recovered components.
Yeah.
And positroid varieties, which are a special type of Schubert variety, are related to the amplituhedron and particle physics.
Exactly. Positroid varieties have this special structure that somehow describes particle scattering. So understanding how to recover them from their projections could help us understand the amplituhedron and its connection to physics.
So where do we go from here? What are the big open questions that need more research?
Well, one of the coolest questions is, can we understand the recovered variety for positroid varieties even better? Can we predict exactly what those extra components are and how they relate to the structure of the positroid variety?
Yeah, like a dictionary that connects the properties of a positroid variety to the specific recovered components.
That would be huge. And it could help us understand the amplituhedron and scattering amplitudes even better, showing how math and physics are linked.
And we could look at the recovery problem for other types of varieties too. We focused on Schubert and positroid varieties, but there are so many other varieties in Grassmannians.
Definitely. Like varieties based on determinants or varieties related to representations of Lie groups. There's so much to explore, and it could uncover new connections between math and physics.
And we need better algorithms for computing those Chow Lam forms and recovered varieties. The methods in the paper are a good start, but when the varieties get complicated, the calculations get really tough.
For sure. Better tools for computation would help with research and could even have practical applications in things like computer vision and robotics.
It sounds like there's a ton of exciting stuff to explore in this area of math. So many possibilities for future research. This paper was a great introduction to a fascinating topic. Well, that's it for our deep dive into the world of Chow Lam recovery. We hope you enjoyed it and maybe even learned something new.
If you have any thoughts or discover anything cool, let us know. Happy exploring!
Okay, so today we're diving into this paper all about the Chow Lam form.
Sounds a bit intimidating, right?
Yeah, maybe a little bit, but it's really about recovering geometric objects,
Yeah, from their projections.
which I think is super fascinating.
It is. It's like, can we figure out what something looks like just based on its shadow?
Right, exactly. And the paper is by Elizabeth Pratt and Kristian Ranestad. It uses this thing called the Chow Lam form as a tool to figure out when and how we can actually do this reconstruction perfectly. And
It gets really deep into some advanced math.
it does, but I'm ready to tackle it.
Me too. It's a beautiful area of algebraic geometry.
So to start, can you give us a bit of background? What exactly is the Chow Lam form and where does it fit into this whole idea of projections and reconstructions?
Okay, so imagine we have some geometric object, like a curve or a surface, sitting inside a larger space.
Okay, I'm picturing it.
Now, we can project this object onto a lower dimensional space, kind of like shining a light on it and looking at the shadow it casts.
Right, like a 3D object casting a 2D shadow.
Exactly. Now, the question is, can we go back from the shadow to the original object? Can we reconstruct the object perfectly just from its projection?
That's the challenge.
Exactly. And the Chow Lam form is a tool that helps us understand this process. It's a mathematical expression that captures essential information about the original object and its projections.
Kind of like a fingerprint.
Exactly. It's like a fingerprint that can uniquely identify the object, or at least tell us a lot about it.
So we have this object, we project it, and we use the Chow Lam form to see if we can go back to the original.
Exactly. And sometimes it works beautifully and we can perfectly reconstruct the object, but sometimes it gets trickier and things aren't so straightforward.
I'm guessing that's where the interesting math comes in.
You got it. Now, before we dive into the specifics of the paper, we need to talk about the stage where all of this is happening. The Grassmannian.
The Grassmannian, what is that?
It's a fascinating mathematical space. In the Grassmannian, denoted KKN, each point actually represents a k-dimensional linear subspace sitting inside an n-dimensional vector space.
Okay, so instead of points, we're thinking about entire subspaces.
Precisely. Think of 3D space. A point in the Grassmannian GR23 would represent a line in that space. It's a way to organize and study all possible lines.
Ah, I see. So if we wanted to study planes in 3D, we'd be looking at GR33.
Well, technically, yes, but GR33 would just be a single point since the only three-dimensional subspace of a three-dimensional space is the space itself. It gets more interesting when k is smaller than n.
Okay, that makes sense. So back to projections. How do we project from one Grassmannian to another?
Good question. It involves matrices. If you look at equation 1 in the paper, it shows how a matrix Z with n rows and r columns induces a map from GRKN to GRKR, where r is less than n. This matrix essentially acts as the projection operator.
Okay, so Z is like our shadow maker, projecting those subspaces down.
Exactly. We take a k-dimensional subspace in the higher dimensional Grassmannian, represented by a kxn matrix, and then multiply it by Z. The result is a KXR matrix, representing a k-dimensional subspace in the lower dimensional Grassmannian.
It's like Z is squeezing those subspaces down into a smaller space.
A perfect analogy. And the Chow Lam form comes into play when we try to figure out if we can go back from the squeezed subspace to the original one.
Okay, I'm starting to see the bigger picture. But before we get to the specifics of how the Chow Lam form works, can we see a concrete example of this projection process in action? It would really help to ground these abstract ideas in something more tangible.
Absolutely. A great example is a curve in GR24. This curve would represent a collection of lines in 3D space, and projecting it down to GR23 would mean looking at the shadows of these lines on a 2D plane.
Okay, so we have a bunch of lines in 3D and we're projecting them onto a plane. What happens to the Chow Lam form of this example? Does it tell us anything interesting?
It does. In this case, the Chow Lam locus, which is closely related to the Chow Lam form, becomes the dual surface of the surface swept out by the lines.
Hold on, dual surface. I'm not familiar with that term. Can you unpack it a bit?
Sure. Think about a point in 3D space. We can associate that point with a plane that's perpendicular to it. This creates a duality between points and planes. We can extend this idea to other geometric objects as well. So the dual surface of our original surface is a new surface where each point represents a plane tangent to the original surface.
So it's like looking at the surface from a completely different perspective through its tangent planes.
Precisely. And in this example, the Chow Lam locus captures the essence of the curve by encoding information about the lines that make it up.
Wow, that's pretty cool. So we've got these projections, this mysterious Grassmannian, and this Chow Lam form that acts like a fingerprint. It's all started to come together. But I'm still wondering about the big question. Can we always perfectly reconstruct the original object from its projection? Or are there cases where we lose information, where the shadow doesn't tell the whole story?
That's the heart of it all, isn't it? And that's what we'll be exploring in detail as we dive deeper into the paper. It turns out that sometimes we can perfectly reconstruct the object, and sometimes we get more than we bargained for. There can be these extra points or components that appear in the recovered object that weren't in the original.
Intriguing. So it's not always a one-to-one correspondence between the object and its shadow. That's a bit disappointing, but also makes me even more curious to understand how it all works.
It's definitely a bit of a puzzle, and the paper does a fantastic job of laying out the conditions under which we can and cannot perfectly reconstruct the original object. It's all about understanding the geometry and the algebra involved.
I'm ready to dive in. But maybe we should take a quick break first to let all this sink in before we move on to the nitty-gritty details.
A good idea. It's always good to pause and let those mathematical gears turn a bit. We'll be back in a moment to unpack the specifics of the Chow Lam form and its intriguing properties. All right, ready to dive back into the world of the Chow Lam form?
Absolutely. That last section was a lot to process, but I think I've got a good handle on the basics now.
Perfect. So moving on, the paper starts exploring these things called Schubert varieties.
Yeah, I remember seeing that term. They sound kind of, well, complicated.
They can be, but they're also really beautiful geometric objects that live inside the Grassmannian.
Right, that space where the points are subspaces. So what are these Schubert varieties, and why do they matter in the context of the Chow Lam form?
Okay, so imagine you have the Grassmannian, and you start slicing it up with these special hypersurfaces called Schubert divisors.
Hypersurfaces. Just a refresher, what are those again?
They're essentially subvarieties with one less dimension than the space they live in. So in the Grassmannian, a Schubert divisor would be a subvariety with one less dimension than the Grassmannian itself.
Got it. So we're taking this already complex space and slicing it up with these divisors?
Exactly. And when we intersect the Grassmannian with enough of these Schubert divisors, we get a Schubert variety.
Okay, I'm picturing it. So we've got the Schubert varieties, but how do they connect to the Chow Lam form and recovering objects from projections?
Well, it turns out that when we try to recover certain types of Schubert varieties from their Chow Lam forms, we get some unexpected results.
Unexpected in what way?
We end up with extra components in the recovered variety, components that weren't part of the original Schubert variety.
Extra components. It's like those extra lines that popped up with the Herzbruch surface example.
Exactly. It's as if the recovery process accidentally adds in some extra pieces.
That's so strange. Why does that happen? Is it like a glitch in the matrix?
Not exactly a glitch, but more like a consequence of the intricate geometry involved. The paper goes into detail about how these extra components arise, but maybe a concrete example would help illustrate it better.
Yeah, an example would be great. I'm a very visual learner.
Perfect. So let's look at example 6.1 in the paper. It focuses on a threefold in GR25, which essentially represents a collection of lines in four-dimensional projective space that meet three specific planes.
Okay, so we have this threefold, our original object, and we're trying to recover it from its Chow Lam form.
Right. Now, the Chow Lam locus for this threefold lives in GR35, so it's a collection of planes in the same four-dimensional space. And when we try to recover the threefold from its Chow Lam form, we get this recovered variety denoted WV in the paper.
And this WV is where those extra components show up.
Exactly. WV contains not just the original threefold, but also three additional components for each of two equivalence classes of Schubert varieties. One class is defined by lines that meet the intersection of two of the original planes. The other is defined by lines entirely contained within one of the original planes.
Whoa, so we're getting a lot of bonus Schubert varieties in the recovered variety. I'm a bit confused about how those just appear out of nowhere. Can you explain the geometry behind it?
Sure, it's all about intersections. When we take a generic plane from the Chow Lam locus, it typically intersects those three original planes in three distinct points.
Okay, I'm picturing it. A plane slicing through the three planes, creating 3 points of intersection.
Right. But here's the thing. In general, there's no guarantee that those 3 points will have a common line passing through all of them.
But they can be scattered in space.
Exactly. But when we impose the condition that the plane in the Chow Lam locus must contain a line from one of those extra Schubert varieties, the geometry changes. This condition forces a common transversal to exist.
Common transversal, meaning a line that passes through all 3 points.
You got it. For instance, imagine that the line is contained entirely within one of the original planes. Now, when a plane in the Chow Lam locus contains this line, it intersects that original plane along the entire line, not just at a single point.
Ah, I see. So we're going from 3 isolated points to 2 points and a line, which makes it much easier to find that common transversal.
Precisely. And the same logic applies when the line meets the intersection of 2 of the original planes.
So these extra components emerge because they create situations where a common transversal is more likely to exist.
Exactly. It's as if the geometry is conspiring to make these extra components appear.
It's mind-boggling. But example 6.1 is just one case. Does this happen more generally with other Schubert varieties?
It does, and the paper formalizes this in Theorem 6.3.
Oh, here comes a theorem. Hit me with it. What does Theorem 6.3 tell us?
It identifies a whole family of Schubert varieties that exhibit this behavior. It says that for this particular family, denoted by a rather complex symbol, the recovered variety will always contain these extra components, these specific types of Schubert varieties.
Okay, I'm seeing a lot of symbols and notation here.
Yeah.
Can we break it down a bit? What do these Schubert types represent geometrically?
Sure. Essentially, each Schubert type represents a collection of k-dimensional subspaces in our projective space that satisfies certain intersection conditions with a fixed set of other subspaces. For instance, one type might represent subspaces that intersect a specific plane in at least a line, while another type might represent subspaces that intersect a specific line at a point.
So these recovered components are basically telling us that when we try to recover these specific Schubert varieties from their Chow Lam forms, we're not just getting back the original varieties, but also these additional families of subspaces.
Exactly. It's like the Chow Lam form is revealing a hidden network of geometric relationships between these Schubert varieties.
I'm starting to see the complexity here. It's like a whole interconnected web of subspaces and intersections.
That's a great way to think about it. And the fact that this happens so consistently suggests there's some deeper principle at play, some underlying structure that governs these relationships. Now, the proof of Theorem 6.3 is quite intricate, involving a lot of combinatorial arguments and cohomological calculations.
Cohomological calculations. I'm not sure I'm familiar with those.
Think of cohomology as a way to capture the topological features of a space using algebra. The authors use these cohomological tools to show that the classes representing those extra components are non-zero, which guarantees their existence as geometric objects.
No, like we're using algebra to prove something exists in geometry.
Precisely. It's a powerful technique that lets us bridge different areas of mathematics.
Okay, so Theorem 6.3 gives us this list of extra components for specific Schubert varieties. Is this a complete picture, or could there be even more hidden components we haven't discovered yet?
That's a great question. The paper is very careful not to claim that Theorem 6.3 is exhaustive. It acknowledges that there might be other components, especially when certain parameters are small.
So there's still room for discovery, for more surprises.
Absolutely. And the paper even puts forward conjecture 6.4, suggesting that the components listed in Theorem 6.3 might be the only ones for a certain range of parameters. If this conjecture were proven true, it would give us a much clearer picture of the Chow Lam recovery process for this particular family of Schubert varieties.
It's amazing to think that even with all this complex math, there are still open questions and mysteries to unravel.
That's the beauty of mathematics. There's always more to explore, more connections to discover. Now, the final section of the paper takes a fascinating turn, linking the Chow Lam form to something completely unexpected: particle physics.
Particle physics. Now, that's a twist I didn't see coming. How on earth does the Chow Lam form connect to the world of subatomic particles?
It's through these things called positroid varieties, which are closely related to the positive Grassmannian.
Okay, now you're just throwing fancy math terms at me. Break it down. What are positroid varieties, and how do they relate to particle physics?
All right. So positroid varieties are special types of subvarieties within the Grassmannian that have a very particular structure. And the positive Grassmannian, as you might recall, is a subset of the Grassmannian where all the Plucker coordinates are positive.
Vaguely ringing a bell. Plucker coordinates being.
They're basically determinants associated with the subspaces. Don't worry too much about the technical details. The important thing is that the positive Grassmannian plays a crucial role in describing scattering amplitudes in particle physics.
Scattering amplitudes, like how particles bounce off each other.
Exactly. And it turns out that understanding the projections of positroid varieties is really important for understanding a fascinating geometric object called the amplituhedron.
The amplituhedron. I've heard that term thrown around, but I never really understood what it was. Can you enlighten me?
Well, imagine a geometric shape, like a polytope. but living in a much higher dimensional space. The amazing thing about the amplituhedron is that its volume directly calculates the scattering amplitude for a particular particle interaction.
So instead of doing all these complex calculations, we just measure the volume of this shape. That sounds way too simple.
I know, right? But that's the beauty of the amplituhedron. It provides a completely different geometric way to think about scattering amplitudes, bypassing all those traditional methods.
It's like a shortcut through the complexity.
Exactly. And here's where it all ties back to the Chow Lam form. Understanding how positoid varieties project is crucial for studying the amplituhedron, and the Chow Lam form gives us tools to analyze those projections.
Wow, so the Chow Lam form, those extra components, they're not just mathematical curiosities. They actually might help us understand particle physics through the amplituhedron. It's like a whole chain of connections.
It really is remarkable. And the paper highlights this connection in Corollary 6.7, which shows that certain positoid varieties also exhibit this phenomenon of having extra components in their Chow Lam recovery, just like those Schneubert varieties we talked about.
So it's not just a coincidence, it's a pattern that seems to be popping up in different contexts.
Exactly. And that suggests there's something deeper going on, something fundamental about these projections and reconstructions that we're only beginning to understand. It's a testament to how seemingly disparate areas of math can intertwine in unexpected ways.
It's like a hidden web of connections, with the Chow Lam form acting as a thread that guides us through it. This entire deep dive has been mind-blowing. I'm starting to see how the Chow Lam form is more than just a mathematical curiosity. It's a powerful tool for revealing hidden structures and relationships in geometry and beyond.
I couldn't agree more. It's a testament to the power of mathematical exploration, how asking seemingly abstract questions can lead to unexpected connections and insights into the nature of reality.
So we've explored all these intricate details of the Chow Lam form, projections, Schubert varieties, even the amplituhedron.
It's been quite a journey through the abstract world of algebraic geometry.
And it's amazing to see how it all ties together. But before we wrap up, I'd love to hear your thoughts on the bigger picture. Like, why should we care about all this? What's the significance of this research beyond just the math itself?
That's a great question. I mean, on one level, this work really pushes the boundaries of our mathematical understanding.
Right. It's like exploring a new mathematical frontier.
Exactly. It's uncovering these hidden structures and relationships within the Grassmannian and challenging our intuitions about how projections and reconstructions work. But beyond that, this research has potential implications for other fields as well.
Like what?
Well, for instance, the fact that different objects can sometimes have the same Chow Lam form, it really highlights this inherent ambiguity in recovering objects from their projections, which is a crucial thing to keep in mind in fields like computer graphics or data analysis, where you're often dealing with projections of higher dimensional data.
Yeah, it's a reminder that the shadow doesn't always tell the whole story.
Right, you can lose information when you project, and the Chow Lam form gives us a way to think about that more carefully. It helps us ask the right questions about when we can and can't reconstruct an object perfectly.
It's like we're becoming more sophisticated detectives, looking for clues and understanding the limits of our deductions.
Exactly. And then there's that amazing connection to particle physics, the fact that the Chow Lam form gives us insights into the amplituhedron through those positoid varieties.
Yeah, that was mind-blowing. It's crazy how these abstract mathematical ideas could actually help us understand fundamental physics.
It really highlights the interconnectedness of math and physics, how seemingly esoteric concepts can have profound implications for our understanding of the universe.
It's like we're discovering a new language for describing reality, a language written in geometry and algebra.
And the Chow Lam form is one of the tools that's helping us decipher that language. It's an exciting time to be working in this field with all these new connections and possibilities emerging.
Well, I have to say, this deep dive has been one of the most thought-provoking and challenging we've done yet. It's really opened my eyes to the power and beauty of mathematics and how it can shed light on some of the deepest mysteries of the universe. Thank you so much for guiding us through this incredible world.
The pleasure was all mine. It's always a joy to explore these ideas and share the excitement of mathematical discovery.
To all our listeners out there, we hope this deep dive has sparked your own curiosity and inspired you to explore the world of math further. Remember, sometimes the most abstract ideas can lead to the most profound insights. So keep asking questions, keep exploring, and keep diving deep.
Until next time.